Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model.
Good morning, everyone, and welcome to our WeAreDevelopers Machine Learning Day. My name is Seat, and I will guide you throughout this day. Today, we are going to talk about machine learning. Obviously, we will talk about how to monitor your machine learning models. We will talk about computer vision. We will have a nice session for the beginners to see how you can get started quickly with machine learning. And we will talk about deep learning for drug discovery. Before we start, a very short reminder. We have just announced our JavaScript Congress, which will take place virtually at the end of November. So if you want to level up your skills in JavaScript, make sure to check it out and grab your early bird tickets. You have a link on the landing page itself, but also here you can see it on the screen. Then coming back to this day, as always, please keep engaged, be engaged with us in the chat, ask your questions to the speakers. We will be happy to have a short Q&A session after each talk, so you can engage with the speakers and get some answers to your questions. As always, we have a code of conduct, which basically means that we need to be nice to each other and treat everyone with respect. Here is a short video to explain it. Okay, with all of that said, it's a pleasure to announce the speaker for our first session. She has almost 10 years of experience in developing scalable machine learning models, bringing them into production. She currently works as the machine learning lead engineer in the data science group of the German online bank DKB. She previously worked at Zalando, where she was working on deep learning models for more than 32 million users. So that's quite impressive, and we are super happy to welcome Lina on stage.
Hey, nice
Hi,
to meet
Lina,
you.
how are you?
Excellent. Thank you. How are you?
Oh, that's good to hear. Lina, can you tell us briefly what we are going to learn from you today?
Yes, I'd like to talk to you about monitoring machine learning models. So I will talk to basically the novice developer who now has to monitor a machine learning stack or is interested in running his own, and what are the key things that you can do and how you can do it with your existing monitoring infrastructure.
That sounds like a lot of fun. Lina, I won't take any more of your precious time, so please have fun, and the stage is yours.
Awesome. Okay. So today I want to talk to you how you can figure out if your AI or your machine learning model is working, but actually returning you less than ideal responses. And what you need to do, in addition to traditional software monitoring, to figure out if that is the case, and so you can address it. So I was already introduced. So I'm the lead engineer at the German Internet bank DKB for machine learning. And I used to work at Zalando before. You can add me on Twitter if you want, or on LinkedIn. So the bank I'm working at is has quite a nice business model. So it serves to providing loans, mostly for daily activities of companies, retail clients, but also small cities. So more like a mission-inspired bank. Also has quite a few investments in sustainability. So I'm quite happy to work there. Okay, so let's talk about the agenda. I will talk to you about defining the business problem and why this is relevant for our machine learning monitoring. I will show you an example problem that we have something concrete to talk about that I have for my job, and what the difference is between the machine learning metrics and the metrics we need for the monitoring of the machine learning models. We'll talk a little bit about the stack you can use and what signals you should use and my suggested order of priority when you implement them. And I will sum it up to give you the takeaways. If you have questions, unfortunately, with this format, I cannot see you, but we have some time for Q&A in the end. Okay, so why should you care as a developer about defining the business problem? Well, with pure software applications, we usually define the requirements, how the application should behave. You all know the jokes about, the comics about the requirements, what the customer wants, what you implemented, what they finally got. So we know it's not easy to write good requirements, but it's comparatively straightforward, and people definitely attempt to write down what the ideal outcome should be. However, in machine learning applications, there's often no properly defined requirements, or they are vague and underspecified. So people, for example, say they want a personalized recommendation, but not really sure what that means. What is it? How is it good? What does it do? Or they say something more straightforward. I want a face detector, but what is the requirement? Does it have to work with any lightning condition? Does it have to work with when you only see half a face, or you see the face in the profile? So sometimes the requirements can be a bit underdefined. So monitoring can actually be more difficult if it's not fully specified what the model should do when it's properly working. So what you need to make sure when you start designing or implementing the solution, or when you get a solution that you're taking over, that you know what success actually looks like, and you spend some time understanding the business case and the success KPIs. I put you a link to a project checklist for ML in general that you can use to see if you properly understood what the context of this service is, so you know when it's working. Okay, so let's look at a concrete business case that I brought you from my job. So in this case, we're having loan requests that are sent to us via a platform. So platform can be, for example, price comparison platforms that call in the background multiple banks. And they in turn call a credit agency. In our case, in Germany, this is called Schufa. And we have two brands, the SKB Bank and the DKB Bank, and we persist the credit response, credit service response in a cache. But as you can imagine, that there are many requests to all these banks in the background, so the take-up rate is very low, and we're introducing a lot of costs. So 90% of the requests for our private loans come from these platforms. There's a low take-up rate, so we are incurring a lot of overhead money costs every month for the credit reports. So what the machine learning model now could do is, it could try to understand which loans are being rejected with a high certainty. If we knew that, we could reject these loans immediately before calling the credit score agency, and we could save these high monthly process costs. Okay, so now we will look at defining the machine learning problem, in this case, in the metrics we use to train this problem. So in this particular case study I brought you, we look at applications from the last n month. So it could be 12 or how many data you have. And unknown is the credit agency response. For example, existing loans at other banks, the credit score, and special events like account cancellations. And then you have a bunch of input fields. So sometimes you hear about input data monitoring. We will cover that later. Here you have input fields, for example, rent, family status, employment status, but you also have the data, the configuration data from the bank, like the current risk configuration, some limits, for example, on age, and some other fields, for example, the type of loan, the platform you have. And what you want to predict is if a loan was requested, rejected, or accepted. So what is actually a machine learning metric? If you sometimes read machine learning literature, you know that we evaluate the model quality by measuring certain metrics. The metric choice typically depends on the problem. There are ranking metrics like NDCG, but also metrics, for example, for binary predictions like accuracy, precision, or recall. So what really depends on the problem you have, then you choose the metric. For loan optimization, we are trying to predict the probability to reject a certain loan. And as a metric, it's useful in this case to choose precision and recall. You actually might know precision and recall from information retrieval. So the precision is how, given a certain threshold for the probability to reject, how correct are you when you predict rejected? So let's say I have a loan and I'm pretty sure that's rejected. We're predicting with a certainty of 90%. So everything above 90%, let's say we're rejecting. So given the threshold, how correct are we? And then we have the recall, given the threshold 80%, what share of the actually rejected applications can we correctly identify with this model? So this is pretty useful in business because if we manage to get a really high precision and at the same time correctly identify a big share of the rejected application, then we could save a lot of these costs. So stay with me through the business case. I'm walking you through that so we have a concrete example for the monitoring, but the tips I will give you will apply to any problem. So here I will show you the precision recall curve. So this means typically when you are very, very certain, you're covering less share of actually rejected loans. But if you want to be like a little bit less certain and it's okay to make some mistakes, you can cover a higher share of the rejected loans. So it's typically a trade-off. And the line that you see here is a prototypical line from a blog post that I linked. So the line will be given by your model. So it can look slightly different. It's a very good model. It's higher up. If it's a worse model, then it's a little bit lower. So for example, here for this use case, we could say we want to be very sure and say we want to only achieve a precision of 97%. And then we can have a look, okay, which recall can we achieve at that precision? And then we are, let's say in this example, which is not our correct number, just for you as an example here, we would achieve 37% of the rejected loans we could identify with this threshold. Which algorithm are we using for that? So all of you hear about deep learning all the time, but actually in tabular data, so this means a lot of numerical columns and also some columns with just types in there. So we call them categorical columns, work very well with gradient boosted trees. So no need to work with deep learning. So the gradient boosted trees train much faster and gain an equal performance. So what you can see here is graph of how it practically works. So the first top left, what you see, the blue is the data, and the green is the model that fit the data. So we have exactly one predicting variable, which is the x-axis, and what the y-axis is the target in this example. and the green line is the model that was fit. So for example, if the x-axis is at minus 0.4, this model would predict a, let's say, 0.5. So you can see the green line is not perfectly fitting the blue data. So in the next step, we will add an additional model, which will try to fit the error that is left from the first model. This you see on the lower left. And what we then do is we combine all the models and have a so-called ensemble, which will then give the final prediction, which you see on the bottom right. So this is the two models combined with their prediction, which is already a better fit for the blue points. So this was probably a bit fast to understand. It's just a rough overview. If you're interested to learn how this algorithm works, I recommend to you the book Hands-on Machine Learning by Aurélien Guéron. And so you can read up a little bit how the theory works, since we're covering mostly monitoring today. Okay, so let's talk about the stack you need for monitoring. So it depends. I brought you two scenarios. So you're either starting from scratch with a pure data science product and you don't have a team, maybe you mostly have data scientists and there's no engineering team and no existing infrastructure. In this case, I would recommend to you to evaluate some full-featured machine learning platforms like SageMaker, or if you already have Kubernetes cluster, maybe you want to look, and it's a big use case, corporate really big, then you might want to look into Kubeflow or Selden. But however, if you already and have an existing platform infrastructure for monitoring and alerting, so you have an engineering team in the company and you have, for example, Grafana as a service, and maybe you have a Prometheus, then you can use your existing stack for monitoring and metric collection. Maybe you need to add a job scheduler, but even you can start with scheduling jobs in a simple way. So what's the advantage of using your existing monitoring and alerting stack? So it's probably really nice that you don't need any new tools. You don't need to maintain them. You can start immediately with the ML monitoring. And I can tell you from experience that it is usually sufficient. So when I was at Solano, which was a really, really big company with millions of users in real time, many, many requests per second, then even us, we did not do that much ML debugging that our typical stack of Grafana and our custom in-house solution for alerting and pulling metrics, that was enough. If you need to do a lot of ML debugging, you will then over time understand your needs and then figure out some custom solutions for what you need. And the nice thing about using your existing dashboarding is that you can integrate with your other metrics, for example, about latency on the same dashboard. And last point, it's also important to note that the machine learning tools develop really fast at the moment, and many of them are not quite mature yet. So it's nice to wait a bit and see which one makes it and comes out on top. Okay, so let's get to the details, what actually you should monitor. So generally, I recommend to you to work backwards when implementing monitoring. What does backwards mean? So you start with the impact in the very end, what is exposed to the customer. So you can compare, for example, the outcome versus the prediction and calculate some metrics on that. If that is not available, so I will go through all of these points in the coming slides. If that is not available and you have more time, you can also look at the service response after post-processing and some stakeholder concerns. You go then to the model output monitoring and some quality heuristics. You also can monitor the features and the general input data before the features. And from terms of priority, I really recommend to you to start at the most impactful one to the right. And then when you have more time, add additional monitoring that will help you debug after detecting that something went wrong. Okay, let's walk through them one by one. So many people get super confused when they read about ML and hear about all these metrics and kind of think, can I not use these metrics that I use in the training process for the algorithm also in production? Well, it kind of depends. So typically for the machine learning metrics, you need the ground truth. You need the final outcome. So in the case of precision, that's why I gave you a concrete example so we can walk through a use case. In the case of precision, you need a correct prediction and you divide them through all prediction to have the share of your correct predictions. But in production, you have the question, how do I get the correct prediction? For example, in the case of loans, if we reject an application, we do not know what would have been the outcome otherwise if we hadn't intervened with our machine learning model. So would this person have been rejected or not? So this can be a problem. So this is the requirement to use machine learning metrics also in production monitoring is that you know the correct outcome and you know it close in time for real-time monitoring. So sometimes you have this case, like I just told you, that you actually just don't know the correct outcome because, for example, you intervened with your model. This is the case for the loan application I'm today showing you, but also the case for fraud prediction. If someone is rejected because we think it's fraud, then we do not know if maybe it wasn't fraud and maybe this person was a legit customer. There can also be the case of a delayed outcome. So if we, for example, predict delivery times for a package, we don't know the true outcome. We only know it a few days later. Let's say it's closed delivery and not food. So for food, you probably know it like an hour later, but that could still be an unacceptable delay for prediction. And then you have the filter bubble effect. So the algorithm decides what to show to a customer, and you can actually not know what the performance would have been on the best option because the best option is unknown and cannot be evaluated. It was never shown to the customer. So if you can, you should monitor the correct outcome. That is the best signal if the algorithm still works. It's exactly what was trained on in the development phase. So what you do is you store the prediction and you store the outcome. And then you calculate the machine learning metrics used during training, for example, as a batch job, or you can create an endpoint to receive a feedback call to your service and expose the metric from there. And you add the metrics to the dashboard and you alert. So in some cases, you actually do know the correct outcome and it can be close in time. So in our loan case, I just told you, we actually don't know if we reject a person. So what we did is we created a so-called holdout set. That means we have a share of the traffic that is predicted, but it's never rejected. So basically, we don't touch it, like a small share of the live traffic that's never touched. And for these people and these applications, we know the prediction of the model and we know the correct actual outcome. And we can then calculate the metrics used during training and compare them to the production metrics. And next, I can show you our Grafana dashboard. It's just a part of the dashboard, so you can see it a bit more clearly. So we have the recall, so the share of the correctly identified applications, and we have the precision. And there you also see a red horizontal line. That's the alert that goes off. So if the precision goes under this line, we get an alert and we can have a look if something is wrong. The next thing I would recommend to you as a priority one is stakeholder fear signals. That's what I call this. So we are usually very excited about the upside of the machine learning model, but the stakeholders are also sometimes worried about what could go wrong. So, and we really need trust when we work with them, since machine learning is a little bit of a new topic to many stakeholders. So what I typically recommend you do is you ask the stakeholders for their worst case scenarios. And then you put these metrics into these fears into metrics to make sure that you would detect if some of these scenarios that they're worried about would happen, and you add metrics to the dashboard and you alert. So for our loan applications, we ask them, okay, what do you think could go wrong if we put this project into production? Actually, we do not want to unfairly reject people. Okay, that makes sense to us. So we covered this with the holdout set monitoring. And then they said, actually, I think maybe this machine learning model, it could be slow. Could it be slow? And well, since we are software engineers, we know it will not be slow, but the stakeholders don't know that. So we took their concern, and well, this is already covered with our typical latency monitoring, and we prove, well, it's in your speed requirements. So in this case, their concerns were already covered with what we planned, but in some other applications, stakeholder had additional concerns. For example, if the service is not available and fails permanently on a certain input, what will happen? Will there be a manual intervention? How will this specific request be treated then? So by talking to them about their concerns in a broader business sense, not just the pure model performance, you will get a lot of insight what is mattering to them and how to not fuck up. I mean, it's great if the model works, but if they have a specific case that they're worried about and you don't cover them and you also don't detect it, you will lose a lot of trust for your machine learning application. So to me, these fears are useful to include in our monitoring and business thinking when thinking about how to monitor this business-related service. Okay, so then we come to the priority 2. In my tips to you, you could monitor the response distribution. This is especially important if you cannot know the true outcome. For example, in my previous company, we worked on recommendation, so there was no true outcome available. So you can look at the response distribution. This is a really good catch-all technique because the response is in the very end before you return to the customer. And so if something suddenly shifts there, it's a good indication that something happened and you might want to investigate if that is problematic or not. So for example, sometimes you return a score, like a numeric distribution. Sometimes you return a class. So that's what you want to see if that changes dramatically. Or over time in case of the score also, that's called a drift. So the good news in monitoring the response, that is quite easy to do. Often it's just one or a few outputs. And it's also very nice that it is usually related to impact. So if your inputs change and you detect that, let's say, one of your 70 input fields has a drastic change, you don't know if this is very relevant for the output. So the output might not change all that much if that field is not important. So by measuring the output, you again are close to the impact, and that's what you want to detect. And how do you detect that on a practical level? So there are 2 types of metrics you can employ. So there's rule-based metrics. For example, you can see that the median didn't change a lot. You can look at quantiles, let's say 90% quantile. You can also look at the share of missing values in fields, empty values. And there's also statistical distance metrics. These compares 2 distribution. For example, Kolmogorov-Smirnov statistic and the D1 distance, or in finance, we often use the population stability index. Maybe you want to see one of them in practice. So I give you one example. This is from a paper from Google, Data Validation for Machine Learning at CISML 2019. So what they do is they have this metric called D1 distance, and they compare 2 distributions. Let's say yesterday's score distribution to today's score distribution. And yesterday is a white histogram on the left, and in the middle you see the black histogram, and it's binned. And you see that the size of the bins is slightly different. So in the first bin, there are more requests with this value. And in the middle bin, let's say this is a medium amount, then you see, okay, that's actually a bit less now. And what you see on the right is they compare these. What is the absolute difference of the size in these bins, and they sum them up, which is basically they compare two histograms to each other. And that seems to work pretty well for them. It's a bit hacky. There's no huge theoretical foundation for that, but as they've proven it and used it very well in their infrastructure, they see that, for example, this kind of heuristic works pretty well. Then I would recommend to you as a priority 2 when monitoring machine learning applications to use quality heuristics. So you create a heuristic which is human understandable and serves as a quality indicator. For example, a really bad response or a really good response or some common sense heuristic. You have to make it use case specific. So the metric doesn't have to be an objective great quality indicator. It just has to go down if the quality goes down. So it's important to remember that when monitoring, we do not aim to measure the objective quality of the algorithm. We just want an indicator variable that changes when something bad happens. So for example, a common sense metric for a personalized algorithm would be the share of responses that are actually from that personalized algorithm. Sometimes we don't know the user or the page or the type of content they require. There's not enough articles to recommend. So the share of personalized responses would be a good indicator. If that goes down, something is probably wrong. You can also have bad experience metrics. For example, users that you serve an empty response or that the algorithm serves a fallback. If that goes up, that's definitely bad. And I can also give you a nice metric from a Spotify talk that I heard a while ago. So they have a common sense metric for their personalized homepage ranking. If you're a user and you have a favorite kind of carousel that you use a lot, a favorite box in that homepage, they look where the algorithm ranks that specific box. And it goes without saying that if that's your favorite, a personalized recommender should probably not rank that low, but rank that rather high. So that's a nice sanity metric that you can put on a board, the average rank. Okay, and then what we can also do as a priority 3, if you still have some time, we can monitor, we can even go further back in the picture that I showed you and monitor the input and the features that go into the model. I recommend to you that you do this at least manually during launch. This has a priority 1 because there are often differences. When you train, you have a certain data pipeline, and that differs from the online pipeline. Often that's different data sources and also different code that processes and creates these features. So there are differences, and you should log them and manually compare them one-on-one or the distribution. And if you have some time, you can automate it and set alerting and tune alerting on that. So basically the difference between training and serving is very important. Google mentions this in their rules of machine learning. And they say they had a really nice uplift also when they implemented that on YouTube not that long ago. So you see even the big, very professional companies have these differences. It's just very common and hard to test and keep these two separate pipelines in sync. So you wanna have that automated. And what you also want to do is you want to compare the distribution in the production over time. A sudden shift, again, can indicate a problem. So you can use the same metrics that I told you before for the outcome distribution, so rule-based metrics and also statistical distance metrics if it's a numerical variable. Okay, so let's bring it together with the takeaways. So machine learning monitoring is often done without the traditional machine learning metrics. So on the left, you have the metrics to train the model, and their goal is to measure the absolute model quality. So you have precision, recall, and so on, depending on your use case. They usually require the final outcome to compare the prediction against the outcome. And in production, the outcome is often not available, or it's not available fast enough So you can actually still do it to see a problem. For example, if it's 1 day delayed, or maybe it's even 7 days delayed, you can still slap it on the board, but it's not, it will not cover all your problems. For example, if you release a buggy stack and you only see it 7 days later, you obviously need additional metrics to cover that case. So that's why you have on the right the metrics for monitoring machine learning models, which their goal is to detect a problem, not to capture the absolute model quality. And that's nice because these indicator KPIs can be created much easier, and also be monitored easier than if you have an absolute correct quality KPI. I would recommend to you to work backwards. So you first look at outcome versus prediction, so the ML metrics, if you can get them. If not, you monitor the service response after all the post-processing steps in the service and some stakeholder concerns. If you still have time, you monitor quality heuristics, and also you model the model version. I assume you already have the model version somewhere else, but put it on the board also. Then you can also monitor the calculated feature in the raw input data to your model, but this is more to help you understand what actually went wrong when you detect it on the outcome side. So to sum it up and bring it all together, you monitor the correct outcome, you implement additional features from the right to the left if you still have more time. And the very good news is you can use your general software monitoring tools that you already have. And if you're interested, I gave you some follow-up links that you can check out. I talk about the types of bugs that typically occur in production. And you have the ML project checklist von Hands-on ML. And there's a really nice slide deck from UC Berkeley on deployment and monitoring. I also put you a link on the machine learning ops Slack channel, where I'm also active, and a lot of other really nice people that work in ML ops and are interested in the topic. Okay, thank you very much. That's it. If you're interested, I'm also looking for some people to work with me. Some of the jobs require German skills and others don't. So check it out. I put it on the slides here at DKB. You can also approach me directly if you want to work together. Okay, thank you very much. These are my contact details. Get in touch. Thank you.
Hi, Lina. Thank you for a very cool presentation. I think there was something in for everyone. And I would say that we just jump in right into the questions. Okay, let me see. Piotr, yes, the talk is live. It's not pre-recorded, but you will be able to watch a recording later if you jumped in too late. So no worries, you can watch everything on demand. Then let's see. Maybe related, as you said, like you are also looking for some new colleagues. Mirko is asking, how do you start to work on these projects? What are the usual requirements and education that you need for that?
So we have a range of colleagues. Some come from a computer science background and got into machine learning by doing courses, doing freelancing, working in companies. Other colleagues come from an academic background, and they have knowledge in programming and also got into machine learning. And so I would say it's a mix.
Okay. Yeah, Mirko, maybe you just check out also like the jobs itself. I'm sure that there are also the requirements. Then Klaas has an interesting question regarding the delayed outcomes. What would be the best way to keep the delay time lower? Or is there any way to optimize?
Well, usually that's given by the business problem. You cannot influence that. For example, if you do predict package delivery, you cannot make the delivery van any faster. So maybe you can get the data faster if it's uploaded with a delay somewhere, but that's what you have to work with your machine learning, like the business case. no way to make that faster.
Okay, thank you. Svenja is asking, in the loan prediction example, how did you train the model in the very beginning when you have no data?
That is usually a problem. You cannot train a machine learning model if you have no data.
Okay, but usually
So
you
you have
can
to
get
wait.
some test data, right? For other examples.
Well, what do you mean?
I think the question is towards like when you start training a model, then obviously you need to feed it with some data. But if you have no data, you
Yes.
need to kind of get some test data or historic data from somewhere else, right?
Yeah, we have all the historic loan data. That's what we use to train. If you have no data, you probably can't fit a machine learning model. Sometimes you can, for example, in image processing, you can use existing models and maybe label, let's say, 200 examples by hand. There are some kind of areas in machine learning where that would work. Where when you start learning the algorithm from scratch, that usually doesn't work. So data is usually required.
Okay, yeah, we had last week a machine learning talk from Alex Waldherr, who is also going to talk today. She, for example, showed something where she needed pictures, and she just, took pictures from Google and downloaded everything. So that would be for computer vision stuff, an example, right, would happen. But wondering.
So for computer vision, you have these transferable models that were already learned on labeled data for a long time, and then you can just bootstrap with creating your own data from Google or labeling 150 examples by yourself. That works. But in this case of application where there's no pre-existing model that you just improve a little bit, that would not work.
Thank you. Boris is asking, is there a rule or best practice on how to know how many metrics make sense and how to prioritize them?
So you think about it. Basically, you want to know if something goes wrong, and then you go based on your business case to understand. That's why I stress the business case that much. You need to understand what the model should do. Then you can think of the failure modes and of the ideal cases to develop your metrics. So no, there is no basic rule. It's not like in application development where we go for the 4 golden signals, because we basically try to understand if the model is working correctly for the business case. And since there are no, let's say, 10 set of fixed business cases, there is no 10 set of fixed KPIs for each.
So also,
sorry.
Again, no, I think it's pretty clear that it depends heavily on the business problem, right?
Yeah.
Yeah. Okay. Then questions are keeping coming in. Miss or Mr. Anonymous is asking, I just graduated from mechanical engineering and I'm trying to be a self-taught ML coder. Do you have any advice?
That's a popular field at the moment.
Yeah.
Well, what would I say? So there's many people applying right now. So you definitely have to do some courses and some practical work in these courses and maybe do your own side projects to gain some experience. So to just come and try to make it with no prior record is because it's so popular. It's not possible at the moment. And the demand is huge. So maybe if you start at a smaller company and get where there's less competition, if you're very motivated, you will probably be able to break in, I would say, but no very specific advice. Just educate yourself, do some courses, do some side projects, and it's very competition heavy.
Maybe from a personal perspective, how did you get into this area?
I think I was just lucky that I was a little bit before the popularity curve. I did not do anything ultra specific that makes me cooler than the people who start now.
Okay. Yeah, I mean, that's something that I like we get asked like often by developers, like, hey, I'm a coder or developer, or have some education in computer science, software engineering, and machine learning is still kind of a cool thing. Actually, recently, with the rise of all of the possibilities and some concrete use cases,
Yeah.
but also it's still a black box for many. Like, where do you start? There's so many different possibilities, so many subcategories, and so on.
Yeah. I would.
So
Yeah. So there's two types of people. One is mostly interested by the technical part of making machine learning work technically, but there's not that much use for these people. And also the data scientists who are only excited by the algorithms. So what we're missing is some people who bring it together and actually make it happen. So if you can have an actual project like volunteer, there are some projects that need, I've seen on a CV recently that they did some, working for free on a project that does something actually, for example, for some NGOs. And if you're just interested by the technical part, that's not most of the job. Most of the job is trying to figure how to piece everything together. And people are very excited only by the algorithms or only by the technical parts, will have very limited job possibilities. So most jobs are actually not in just applying the very cool latest things. So I think it's a little bit overhyped, and I hope some people who are actually good with talking to people and finding out what's needed are also kind of getting interested in that.
yeah,
So
so you need to bring
the developer will have to
offers
come back
together.
out from the desk and actually talk to a bunch of people. And so if you're just interested in the tech, there are not that many jobs who will in the future only require that.
Okay, that's interesting. Then Alex is asking about so many questions. Alex is asking, just let me see. It's, what is your usual approach when building the ML part? Do you start prototyping, or how do you do that?
Yes, you look at the problem, you try to understand the business case, and you validate some assumptions about the business case first. Because what the data says and what the people say are often quite different. So you really need to first understand, does the data support the business case before you start prototyping the ML application? And then you kind of already know this kind of problem works well with these kinds of algorithms. And then you just prototype to see a rough idea how good you can get in performance.
Okay, thank you. Then Jürgen is asking, how much of your time do you invest in the machine learning pipeline infrastructure?
The infrastructure. Is it the underlying ML infrastructure or the data cleaning and munging?
So Jürgen, maybe you just can make the question a bit more concrete, and we will be happy to answer it. Let me see, what else do we have? Yes, you will be able to watch it also later on demand, Brian, so no worries. Helen has a question. She says, maybe it's a bit off topic, but how do you manage the stakeholder communication and keep them happy and not going crazy? I think this refers to the part where you said that they are sometimes a bit tricky about the signals and they don't like it as much as we do.
Yeah. Yeah, that's something that is difficult for every ML project to figure out. So you need to understand what their priorities are. I recommend also looking into their fears, like I said. And then we do ongoing updates, nothing very specific. What you can do, you can apply techniques of project management to find out who is interested and needs to be updated, who can do a veto on your project. So you keep a close eye at these people. So this is more or less typical project management, and we're trying to keep it at a sweet spot. Not too much, because in the end we want to work on the project, but not too little. So this is classical project management, I guess.
Okay, thank you. Pick is asking, can you elaborate a bit on gradient boosted trees? Why exactly is it better for prediction, and are there any downsides? I think it was at the very beginning of the presentation.
They're not necessarily, so what does better in this case mean? They're not getting a better performance than, let's say, deep neural networks, but they are faster to train, like a lot faster. And so that's a plus. So that's what we use. And so this goes to show that you don't always need a deep neural network for all types of problems that you have in ML today.
Okay, thank you. Then a couple of questions also for the people who came in later or joining right now. Could you just sum up maybe some good references and books for the people who want to learn more about these topics?
Yeah, I put them at the end of my slide. Maybe we will share the recording, then you can look them up.
Okay.
Maybe I can also, I will paste them. I will try to join the chat. I will try to join the chat and paste them. 1 second. No, that doesn't work because the links don't work. Okay,
so we can do it actually. So we can have a look and do it actually. And Jürgen has clarified the question. Thank you, Jürgen. The pipeline and ML infrastructure question. He said, I mean to create and maintain the infrastructure for doing machine learning like ML ops activities. So how much time do you invest in these kind of things?
Yes, so my team has an ML platform team which does that. That's 2.5 people, I would say, and they run all the services like the Prometheus and the Grafana and like all kinds of infrastructure stuff, some in Airflow soon. So actually a lot of time. That's why I said it. If you start from scratch and you don't have other engineering use cases, I would recommend that you look at these full-featured platforms where you don't have to maintain that, because that can be very time-consuming. And if you're a smaller team or just mostly data scientists, then I wouldn't want to do that myself.
Mm-hmm. Okay, so I see we are already a bit over time. So Lina, is there anything else you want to share with the audience?
No, it was very nice. So thank you for having me. If you have follow-up questions, you can ask me personally, LinkedIn, the MLOps Slack, if you would like.
Okay, perfect. So Lina, thank you so much. It was super interesting to get some insights in the monitoring part also of machine learning systems. I hope to see you soon again at maybe some other occasions. In best case, maybe even at an in-person event. So I wish you a nice day and see you soon again.
Thank you, Thea, to you as well.
Thanks, bye.
Bye.
Okay, this was our first session. Thanks for the many questions and for being such engaged in the chat. We are going into a very short break and we will come back in 7 minutes with our next session about computer vision. Stay tuned and see you in a couple of minutes.
Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model. Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model.
Hey, welcome back again. I'm here with Flo Pachinger, who is a developer advocate at Cisco DevNet and is super interested in IoT and machine learning and network programmability. And yeah, hey, Flo, how are you?
Hi, Sayat. How's it going? Thanks for having me.
Good, good. Thanks for joining us. Flo, what are we going to learn from you today?
So I have got a pretty exciting session, and which is in talks, I think, like a very high topic in high demand, which is about computer vision. So basically about how can you do and leverage machine learning or deep learning capabilities and the technologies with cameras. So basically with image processing, with video processing, and how can you gain the data out of it?
Okay, so we will detect some license plates with you today.
For example,
Exactly.
or if somebody's wearing a mask and so on. So I will show you some examples and how to integrate exactly this technology here.
Okay, very cool. So Flo, the stage is yours.
Perfect. Thank you very much. So hello everybody, and really thanks for joining this session. This is about computer vision from the edge to the cloud done easy. As Seth already mentioned, so I'm a developer advocate at Cisco DevNet, and let me show you a bit more on the agenda and evolve. Okay, what can you learn here? So first of all, I would like to go to the challenges and the use cases on what you see there. So especially about what are the architecture and components of the solution, where you can detect, for example, if people are going through the building or if there is any suspicious behavior there. I will also go a bit about more into our Meraki IP cameras. And then as well, the focus is how to integrate these cameras into the computer vision platforms of the big three. So basically of AWS, of Azure, and of Google Cloud Computing Platform. So basically, I will also do a comparison overview on, especially on the pre-trained models, so on the machine learning capabilities, what are already available out of the box on these platforms. And of course, I will showcase you what kind of projects we already did and how the architecture very much on the technical perspective looks like. So without further ado, I would say let's start here. Just a bit about myself, so just so you know who I am actually. So I'm based in Vienna in Austria, and my background is mostly software and networking focused. So as I already said, so I did a lot of stuff with IoT projects as well. So with smart parking with LoRaWAN, for example, then lots of like a dashboard with lots of sensoric, so LoRaWAN sensors, but then also I will showcase you our Meraki sensors, which are basically sending the data via Bluetooth. And then, yes, I did a cool network monitoring tool, which you can find also on GitHub here. Yeah, if you'd like to know more about this, all the content what I present, you can find us on developercisco.com. So let's start actually. And this is the cool thing. I love to start with the why, because I think this is the most interesting, or let the part of why are we doing this, or what is the outcome there. So what are we trying to solve? And this is basically a good question, right? So let's start with a definition, so that we're in the same boat here. So computer vision deals with how computers can gain higher level understanding from digital images of videos. So from the perspective of engineering, it seeks to understand and automate tasks that the human visual system can do. So basically what you see here is this person is walking around in the store, and the camera is detecting that this guy, basically, this is a person walking around. And this is the tricky part of how can we leverage like the human eye and basically put this analog, what we actually see, these analog sensors, or these analog actions, put into the digital world. And this is exactly the really cool use case, and what we see right now is very high in demand when it comes to computer vision, especially how to gain actual data out of the images. You've seen a lot, for sure, the sensors with temperature sensors, or, for example, open-closed door sensors, or other specific sensors from the IoT world. But then again, the camera itself can be also seen, of course, as a sensor where you can detect and can even do more advanced use cases there. Use cases, for example, so highly like in which sectors could this be? So in retail, for sure. So basically what we've seen just now, store employees get a notification if there are more people or more customers in this area, let's go there. In the education system, or in education, where, for example, are students allowed to be in the playground during the class? Or is there any like children, like is there anything else like happening in the classroom and the camera is detecting it? Also, when it comes to public safety on the right side, so the police or the fire department, they can quickly determine is there anybody in the building? Or we had, for example, a use case like if is somebody blocking the emergency door? For example, if there is a block out there, it can of course risk some lives. So the emergency doors, they need to be clear. Other use cases are, especially you've seen it as well, maybe a bit in the at the transportation, so traffic monitoring for sure, remote site deployment, where you can see, hey, is there a lot of traffic going on or not? Or why is there a lot of traffic? Like then you can go more into the bit and leverage the historical data and can actually determine or can predict, hey, at this day in the next 2 weeks there will be more traffic which is happening on this road, for example. Also building management, so parking lot surveillance. You can see, hey, is there actually a car parked or not? You can also do this with the camera. There are also, of course, like other possibilities or other ways to see if the parking spot is empty or not. But a camera would be also a cool option, and maybe more reliable sometimes, as we've seen with checking if what is happening at the parking space out there. And finally, smart cities. So, of course, perimeter monitoring when they're like in open areas and the streets. So also you can see there, hey, what is happening in my cities there. Apart from that, there are like just examples of use cases. There are, like I said, like in manufacturing industries, it's also nearly the same, where you can detect anything. So now, after the use cases, after the why, let's actually check on the components and the architecture there. So you can see here on the left side here, the scenes are being recorded. So this is basically the image there. Then we have, of course, a camera. So the physical sensor, like which is basically translating the analog actions into the camera, into only images now. So images, basically, it is a bunch of numbers. And then we need to store this video footage somewhere. So there is definitely a storage component. You can store it on the camera, you can store it in the cloud, in your own data center. So this is basically, we need to have it here. And then one important thing is definitely for sure the logic processing. So this is also part, and this is a huge part here now, still very abstract, the machine learning pipeline. And we'll go this then into a bit more. So for example, you need to have, of course, the logic, which is processing what scenes or like what is being recorded or what can you extract from the scenes. And this is called inference. So inference is basically you basically check with your machine learning model if there is a person, for example, in the scenes which is being recorded. And the other two thing, or the second thing, is basically the training of the machine learning model. And this is done, of course, like there you need to have a lot of graphics power or a lot of compute power here. And this is usually done in the cloud or, for example, in your own data center, but you need to have, of course, graphic cards. They're available. Finally, like these projects, this logic processing, so the two parts is with the inference. So this is already built, and then building your own machine learning model. So this is where you need a lot of compute power. Basically, the results, what you see here will be then in the dashboard. So on the dashboard, also a very good or very, of course, interesting component is about, hey, like what can we see, like how many people basically are going through the camera there. So with that being said, so this is the architecture there. Let's go more into a bit on the Cisco Meraki cameras so that you can see, okay, what are the capabilities there and how to integrate. So just all around, so just for you to know, so who are not familiar with Cisco Meraki, this is a cloud managed solution. So Cisco Meraki, with Cisco Meraki, you can manage the wireless access points, networking devices, cameras only via the cloud. So if you go actually there, like locally, you can't do it. Everything is done via this dashboard where you can manage all these devices there. And this is the cool thing, or this is the cool thing, because the cameras as well are super easy to be mounted. So this is why, again, coming to the section, to the title and say easy. So you deploy the camera, you just plug it into the network, and the camera will receive an IP, just needs an internet access, and you see it on the dashboard. So the deployment of the camera, this is the easy part there. Just for you to know, so just to have it in the back, there are several models. So fisheye could be a fisheye, could be outdoor cameras with IP67 enclosure, with vertical zoom. With non-digital zoom. So yeah, so there's some models out there. Then let's go more into the architecture there now. So basically, scenes are being recorded. You see here Cisco Meraki IP camera, which is already doing some analytics there, and then you will see this in the cloud dashboard. So basically, what can you do? The camera footage, the video footage actually is already stored on the camera. So it has like up to 512 gigabytes of storage there. And it can detect out of the box persons and vehicles. So out of the box, there is already some mechanism there. So it's a Qualcomm Snapdragon processor included, where you actually can detect the persons and the vehicles. Also, what's there, and this is also really cool for your own project there, is audio analytics. So basically, it can detect what kind of audio could happen. And this is something what you can definitely have in mind there, that you actually check if there is a fire alarm, for example, in the building. The camera is a microphone there, and it can actually detect, hey, there is a siren going on or some alarm, and then it can record images or even like send, of course, webhooks messages, emails, SMS that somebody's happening there. And finally, you can measure illuminance. So basically, how bright is it? Is it dark right now? Like, is it night or is it during the daylight? So let's go more into the developer interface. And then, as you can see, I'm building this up, then going, okay, how can you interact especially with the big three, with the cloud providers there? So first of all, Cisco Meraki cameras, they have, I said before, like they're usually cloud managed. So with you can do lots with the REST API. You can also deal a lot with webhooks. So basically, if something is happening, the webhook is basically saying, hey, do something there. What you can also do is that we are leveraging MQTT. So MQTT is very important there, of course, to say, hey, a person is walking through the camera or a fire alarm is happening. So this is done locally. So locally, the camera has an MQTT client up there where you can send basically these events out there. Also, I think this is also standard, I guess, or like in lots of IP cameras, you also see that we also have a RTSP stream there where you can here directly, like locally, get the video stream out there. All right. So with that being said, so you saw actually that there are a lot of trigger points there. So, or the trigger point is with the camera. So, and this is before I going now into what is the best to basically interact with them. I will show you a bit about the Meraki camera there. So let me go here to the dashboard. And this is the dashboard of my camera at home. So you will see me now in a bit. So don't worry, don't be afraid. I see here, like, this is the machine learning test cam. I'm clicking on it, and you can see it here now. So this is me talking. What you can also do, you can of course have like the historical things and so on. But the cool thing is that you have already the opportunity to actually enable the RTSP stream here. So if I open VLC, for example, I just copy it, and then I see the live stream already here locally there. Then what other thing, and this is for later on for the demo, it's important to have, you can set zones. So for example, when I create a new zone, I can drag here and say, I would like to say if there are any people in this specific zone. So like here, then please detect it, or like please say, hey, in this specific zone something is happening, then please via MQTT say so. Just for you to know, after I go in there, you actually see that I have here already a priority zone here with me, with the detection overlap of 100%. So you actually see here, hey, there is a person happening. And finally, the sense component, which is the cool part. So you see here that I have enabled the MQTT on my MacBook, MQTT broker on my MacBook here. And you can see here all the specific MQTT topics which are detected. So you see here audio detection, audio analytics, light. And I will show you now what does it mean. So first of all, I am opening up my code. So this is very similar. So I establish MQTT connection. I subscribe to all the, except for the raw detection, I subscribe to all the important things here. And then I actually also, and I will explain this a bit later, I will also save the camera snapshot when a camera is in this specific zone, what I just showed you. So basically, I'm opening a new thread here. This is Python code here, and I'm saying, okay, please do a snapshot of the camera once a person is in there, and actually do something with it. And with that, I will show you in a bit. The other stuff is just the Meraki API stuff. And yeah, you can find the source code, by the way, you can find it online already. But for the demo, let's actually start it. So I'm starting here now. So you can see here that there is already in priority zone is one person. That's okay. You can see the audio level. You can see the looks. So if I'm going more into a dark, so if I'm covering the camera right now, you can see the looks is going down. If I'm going away, it's like 400 again. And the cool part is now let's do a fire alarm, right? So I will need to disable my headset here.
Hey Flo, I think you have muted yourself somehow. Or maybe you have to change in StreamYard now the cam and mic. No. Now we hear you.
All right. Okay. All right. I'm sorry about that. So basically, what I was just saying here is like that. You saw. I hope you saw it. So I was playing a fire alarm here. Fire alarm with multiple sounds. So it's a simple YouTube video here. And you can actually see that, and I'm coming to this in a bit, you can actually see here that there, before that, I hope you saw it, that there was a fire alarm. Let me just stop the script here. That there was, that the camera detected a fire alarm there. So fire alarm in a way of that, hey, something is happening in the specific, in this area here. Furthermore, and you've seen it already, is that the camera actually got the snapshot here as well. So like what I was saying here with this specific code here is that if the person is like, if there is at least one person in the screen, download the snapshot actually and do something there. And I already actually sent the snapshots, and I will show you this here with the images. That I actually saw this one, and it 1 second in the images. So then it must be here. That it detected my my face here. So here you can see that with, and this is done, I will show you then here in a bit, with the AWS recognition, that the snapshot, what was being downloaded actually, and this was just one snapshot, what was being downloaded was actually uploaded, or basically this image was checked against the predefined or pre-trained Amazon face detection model there. And this, like, what did we get back here from that perspective is the following, that we actually got back here via JSON the face details, or the bounding box here where the face is. And you can also detect, okay, hey, like the face detection, the face is between 22 and 34 years old, which is correct. It is gender male. The eyeglasses are false. Emotion, well, I look angry, but calm. Like this is what AWS is at least saying here. So, and again, here another snapshot there. So a bit surprised. So what you see here, and let me go back to the slide so that you maybe can understand the code here, is that the Meraki camera, and let me go into this one here, is basically sending the MQTT images, or like it's detecting that some person is already there. And sorry, this was actually the thing. So the first the person walks into the camera zone. You can see this here in the Meraki camera. So the Meraki camera is then, as a second, pushing via MQTT to the broker to this Python script. So the Python script is receiving this information, and then it's requesting just this one here. And this is the cool thing about this, is requesting just one snapshot there. So just one image. And for you to use is basically the computer vision face detection. So this was, in this case, AWS recognition, will just recognize, or only needs to recognize one image file, and then sends the results back to the dashboard or to the messenger, or as you can see here, really raw, basically the results there. So this is only now for the face and face recognition API. So what you can also do there, so what I did is as well, you can also do some label detection there. So I did this before. You can see that it's like that. You see me, and you see, for example, that this is a laptop or some computer screen, which is also there. So the cool part about this is that, and then I will go back here for an overview, is that via MQTT, so there are several use cases or several architectures what you can use with MQTT, like to get actually the data at first, like a text-based data out there, and then doing the image recognition. You can also, of course, do it immediately via RTSP, so real-time streaming protocol, where you can send every time something is happening, the data via Amazon recognition. Or you can do it via the REST API and webhooks to Azure Computer Vision or the Google Vision API. So you can see here definitely like a really lot is going on. And the thing, like why is it the cool part is the following, that the trigger parameters. So the trigger parameters, and this is something what I think is definitely worth looking into, is to have the inference in the cloud only when something has been triggered. So, for example, if the door is being opened or closed, then the camera is doing a snapshot, and then actually you can see it here. The snapshot will be sent to the computer vision face detection platform, and then it forwards the image as a result to the messenger and dashboard. And this is again, so why is it cool? Because the camera is doing, and this is what it should do, the person detection or some detection there, or for example, working together with some sensor, and then leveraging actually the cloud platforms with computer vision and face detection. And then just for the audio analytics, just to sorry about it that it was on mute. So basically, I was playing an alarm, and this is something what's really interesting is as well is also that, like I said, the camera is a sensor to have also audio analytics there. So that you see actually here, this is on the top, you see here the office, like normal people are talking, the photocopier and so on, like something is happening, like not during Corona, not during COVID, but like hopefully afterwards soon as well. But what if like there's a fire alarm happening, like there's a pattern, right? Like it goes up the serene, it goes down, up and down, up and down. And this repeating pattern, the machine learning algorithm noticed this one, that something is happening, as you can see here left in the background. It goes up and down, up and down, up and down. And then it actually detects, hey, there is an alarm going on. Cool. So with that being said, so this is basically the overall architecture what you can do. And now let's actually focus more on the big three here. So what is the difference? What can you use there? So what you've seen here now, so with the big three, I did also some observation basically about and checked what are the, as of now, and of course they're always changing it, like in October 2021 or getting new feature with pre-trained models here now. What is the difference there? So you can see here on all of the three, the label detection, the image moderation, face analysis, what you interesting, celebrity recognition is actually available on those three platforms, also text and images there. Face comparison, interestingly, AWS and Azure only. And AWS, because it's also going more into the IoT space, I've seen is like personal protective equipment is also there out of the box available. Color of the images, landmark detection, product logos, this is then only available with GCP. Pricing overview, so just to know, so I think it's also cool to understand. So what you can do, especially for testing. So in AWS, you have within only the 12-month tier, you have 5,000 images per month what you can test. With Azure, you have always, as of now, the first 5,000 transactions, as they're calling it, per month for free, and in GCP 1,000 units per month there. So then it depends on the pricing segment. So I just would like to have a feeling there. So first and second price segment, then it's about like $120 per 1,000 images. Then it goes to $0.96 dollars per 1,000 images. And please be aware, like there are different price segments for all these providers. So it's very different because because it's $1.50 here and $1 here. So you would definitely have to check here in detail. So I just put it in here just for reference here that they are the pricing tiers are very different here. Then also I really would like to point this out. So of course this session is called like easy. So with that, I was only talking about the pre-trained models there. So of course, what you could do is you could build your own custom model there. So doing your own updating your own how's it called, like data set, doing your own custom labeling. So for training, of course, and then prediction. But then Amazon recognition, it's called custom labels, then custom vision services with Azure, and then with GCP's AutoML Vision, and AutoML Vision Edge is the new one. So basically, there you can you need to take care of your own data set. Finally, the implementation you have seen. So I used for all of these, all of the references, what I did, I used the Python SDK. So you can see it like in lots of languages, their SDK of the cloud SDK is of course available. And then for the specific use cases for the computer vision platform, they are also in some examples also specific SDKs available. But so far it was really easy to actually try this one here out there as well. Cool. Then, of course, demos and notable projects. What I would like to share here is a colleague of mine did as well the Meraki MV and AWS fast face mask detector. So this is actually done, and this is very similar. What I've showed you before is that the MV camera is detecting the person with MQTT client, sending the MQTT message then to an MQTT broker, and from there it actually the computation, the Python script is done in the cloud with a Lambda function. So basically, it sends the image for analysis with Amazon recognition, returns the response, and then posts it into a WebEx room, so into a messaging room. And you can see on the right top here the output. So basically, it's very cool that you can see that the camera is taking a snapshot once the person is there. You can see the quantity of detected people, and then Amazon is taking care of, hey, is the guy is wearing a mask or not? Another thing is also like the capturing the license plate, and this is a cool use case. And also we've seen it in the US a lot. Is that for example the camera is capturing an image, then here the camera also detects, hey, there is a vehicle going actually through the screen, and is then sending the via API, hey, please at this time frame, at this specific time point, please call the snapshot. And then via a third-party tool, so none of the three cloud providers, but still is basically reading the license plate recognition here, or is reading the license plate, and then you can see, hey, at this time, this license plate actually was going away from the ground there, or from the perimeter. This is also another example what I personally did in our office in Germany. So basically, this is entrance observer. So I was using here the Meraki MT open closed door sensor. So basically, it's an open closed door sensor. And then here again, once it was open, so basically once the door, and as you can see here, the person walking through is open, then the snapshot is being triggered. So here again, this is the important part. Something is being triggered, and only when something is happening, like only something is worth mentioning, then the camera is taking an action to the user. So camera is recording all the time, of course, but still, if there is something happening, only when then the user will be notified, and then the snapshot will be triggered here in this case. So yeah, so with that being said, so this is conclusion also of final slide. So why is this an easy solution, and why was I calling this out? So first of all, everything is in this way cloud managed and reachable via API. So the cameras are cloud managed. You have, of course, something physical there. But anyways, everything, the API is the computer vision platform, as long as with the cameras is cloud managed. The installation of the cameras itself are super fast. So you power on, you connect the camera, and it is there. And also only, and this is the trigger points basically, the only important image data is being sent securely to the computer vision platforms, which are one of those three here. Of course, not limited to them three. So there are like lots of other also smaller providers there. It really depends then on the data set, of course, or what you would like to sense, and what you would like like what kind of data you would like to get out there. Yeah, with that being said, do you have any questions, or feel free, of course, like if you have any specific other questions, to reach out to me. So you can find me on Twitter as well, I guess, or LinkedIn and so on. So yeah, but I'm happy to take any questions, of course.
Hey Flo, thank you very much. Super interesting as always when you are here. Let's jump into the questions, right?
Sure.
So let me see, what do we have here? A personal question from Carlo. Do you use this also privately, and if yes, for what use cases?
Sure. So privately, actually, I am using this for the open door close sensor. I actually don't use it anymore, but I tried it out. So I have it in my home. So if you'd like, I can show you. This is there are no personal data anyways here. So I have actually here in my environment, I have here the open close door sensor. So when I see here in my flat, I actually see here that my front door is closed. And you can see here, hey, when the door was open or closed. So I know if there is any burglars coming in or something else. But I had this once here that this was the trigger point. This is where this camera, what you saw. So I use for test that something is being triggered, and then that, hey, I'm making a snapshot and see, hey, this was me coming in or somebody else. So I had this set up, but then I removed it, because basically this was enough for me. But yeah, so this was my private one. And then just for you to see here, like, I know this guy. This is in Argentina, actually. So he actually did this. So Alex did actually, and you can see here this face mask detector. So this is actually, maybe I'll make it bigger. So this is actually in his backyard, where you can see, hey, this guy, like somebody's wearing a mask or not.
Mm-hmm. Okay, cool. On another note, do you have pets?
No.
No,
As
okay.
of now, no.
Because the question is, I saw you can always, in these camera systems, you can always, mark the zones that you want to be detected and so on. But if you have some pets, like I have 2 cats and they are running around, then it would always trigger a signal, an alarm. Is there any solution to kind of, remove the cats from the system?
That's a good point. So we definitely need to look into detail there, like what is again, what are the trigger points here. But I would say you can detect, like, you get basically back, and maybe I can show this here in a bit. You are actually getting back and I think this must be here somewhere. You can actually back some labels there, what is in the camera and what is not. So just a JSON. So you can actually say, hey, if there is a cat as well, and only a cat, or maybe only a cat, then you don't get notified. Of course, it can happen that Amazon is recognizing it, but which I think in some cases is fine. But if there is, for example, something else happening and there is no cat, or not the parameter, or not the sensing there that there was anything, then you will get notified. So this would be, I think, a good solution there.
Does that work based on the object size, or? So what if you would like to, remove the cats but not the dog?
Right. So it depends on the so for that, it depends on the what you would like to achieve here. So you can definitely see. Let me. I think this should be here somewhere. StreamYard, not you. So for example, when you go to, it's actually really cool implemented there. So when you have here the specific label detection there, then you can see here that, okay, there is a car, there's an automobile, there's a vehicle, a person there. So when you say here, hey, I would like to get the results, and there is a cat and a dog, and I would like to detect only if there is a dog in the picture, like only the dog here, then you can, for example, say, hey, I would like to have only I want to be notified only when there is only the dog there. So you just say, when you get it here, result is dog, perfect. When it's a cat and dog, then you don't get notified. So you will see still in the picture the cat and the dog. That's for sure. But for the notification or from the point of view, you will only get notified when there is only the dog there.
Wow, cool. That's quite sophisticated. Very nice. Yeah. Let's see for some other questions. Max was commenting during the talk that, let me find it, Azure also has landmarks and celebs detection. I think it was not marked in your table. So just maybe.
All right. Okay. Perfect. Thanks for that. Really, thanks for that. So I've as you for sure know, they're always updating this. It's very hard to keep this in always up to date. But no, thanks for that. Then I will add this and check there.
Yeah, thanks, Max. Then Torben is asking, where do you get a set of patterns from, and how do you create your own patterns, or is it just out of the box?
Okay, that's I was kind of expecting this question, so thank you for this question here. So first of all, this is what you've seen here. So this is only computer vision platforms with pre-trained models. So this is everything out of the box. This is the advantage, let's say, of the cloud, because basically it's very important to have a lot of compute, like many graphic cards available, depending, of course, on your workload, in order to detect. You can also do this. So with the pre-trained models, this is all out of the box. But you can also, of course, create your own data set. So when is this needed, or when is this happening? So when you would like to detect something specific to your use case. So for example, label detection is only there are only a limited amount of labels there to detect. So for example, you can detect specific, like a dog, a cat, a person, a computer screen, and so on, but this is limited. But if you would like to, for example, do a specific logo detection, do a specific detection of your favorite mug, for example, or anything else, then you would need to do it on your own. And this is what I did in the, just as an example, in this use case here. Hey, is this table here, and this is the specific glass table here, is this empty or not? And how do you do this? Like in a nutshell, what you do is then basically you create at first this a snapshot, or like this. You cut this out of the table and say, okay, this is empty, this is full, but how to do this? So this is where you can't do this out of the box. So AWS out of the box definitely can't do this. So you need to do this on your own. So you need to use your custom machine learning model there. And for that, you actually create a lot of data sets. So created data sets with lots of empty tables and lots of full tables. And the full, you also need to of course, need to select the different full tables. So for example, if there are glass bottles, if they're not, if there's something else going on there. And then finally, you run this. For example, I did this, and this is very overfit. So a very easy example with Keras and TensorFlow, where you say, "Hey, I create this sequential model here and build it up on this specific use case." And then finally, if somebody is putting there on the table or not, then you can definitely see here something is empty and full. But then again, you definitely need to have your own customized machine learning model for these use cases here.
Okay, thanks. Quite interesting. Okay, tricky question. I'm not sure if you have an answer for that. Chris is asking, how do you distinguish between twins in face detection?
This is a good point. This is I've seen, so if you're following some of the leading computer vision guys or machine learning guys, there are actually, there was shortly on LinkedIn, he posted this, the thing that Amazon recognition didn't recognize it. So he did some example there. He put two twins in front of the camera. Then Amazon did not recognize them. They say it did identical, especially it was for the phone. Where it was recognized, or I think, sorry, it was the from the iPhone, the Face ID. And then it didn't recognize it, so the twins, they could open the phone. But then this guy did a very specific machine learning model there, where he could actually detect at least where something was different from the person, like, and you need to be very specific there, of course. That with the shape of the image, you need to be aware of, like, you need to have a lot of training data, of course, to move the head around to see, hey, maybe there is at least something what we are missing from the human eye, that basically with math, or basically with machine learning, what the machine can figure out there. So it's tricky, very highly topic there. As of now, you definitely need to have a custom machine learning model for that.
But it would be possible, actually, if it's not 100% identical,
yes.
which it basically never is. But okay, that's cool
Indeed.
to know. Then another tricky question from Professor. He's asking, or he's saying, I would like to become rich. Are there any prediction models for roulette? Joke aside, do you know something machine learning related going on in the gambling industry?
So as with that, in the gambling industry, they are, from what I know, highly aware of, especially when it comes to the cameras there. That when you go to the casinos in Las Vegas and so on, like, there are tons of cameras there, that you can actually see from this perspective that if there is some suspicious behavior, that they are actually on it. They are moving more to an automated way, but mostly, of course, there are, like, still humans there, and to see what is happening there. From the gambling perspective, it's again, it's tricky, because with machine learning, in a way, it's learning what, like, the prediction, usually, like in a classic scenario. And from that, you can try it, but when it comes to what will happen in the future and so on, you cannot predict it for sure. So there are some examples on there. What I know is that from the stock market, people tried with machine learning models to predict it to go up and so on. But then again, there are so many parameters and so many possibilities there, and that it's too much of a random. Like, it's too much random to say, like, to have at least like 90% of accuracy there, right? It's very tricky to go for it. Like, there are in some games, I think it should be fine, but when it comes to totally randomness, or like a where the randomness is very high, then it's then also with machine learning, it's like very tricky, or like you don't get an accuracy of, like, with above 90%, I would say.
Okay, thanks. Yeah, I mean, I think in this industry, especially, use cases are probably already, like, using the cameras to detect if there is some fraudulent gaming or something else. So I don't think that there is Robert De Niro and Al Pacino staying there and saying, hey, this guy's counting the cards or whatever, but maybe now with the cameras and some algorithms and some machine learnings and so on. Yeah, quite interesting. Then also one question from Mario. Does it work with any type of cameras? What are the requirements?
Sure. So with that, basically, the cameras is, so you can buy an IP camera is basically you are recording any scene. Usually what you look in cameras, so about resolution, especially when you see if is it dark there, you need some night vision there, these kinds of things. Like, do you need optical zoom, or is digital zoom enough? Do you need, like, from the angle perspective, like a fisheye camera, like where you have the whole room or not? So it really depends at first on what you would like to see, of course. And then from the specific or the difference with Meraki camera is that we put, and this is where I also think is like the market is definitely going, that the processing, and this is why there is a Snapdragon in there, a GPU similar what you have on your phone, is that the inference or like to deploy the model on the camera, this is basically a uniqueness compared to other IP cameras. So that you can deploy, or like there is people tracking, there is vehicle detection on the camera. Usually, like the classic solution would be you store the video footage somewhere remote, meaning in the cloud, meaning in the on-prem, and you also do your analytics remote or in the cloud. But then for every image what you do, or for every when a person is coming or like when anything is happening, you need to send it. And this is sooner or later, I think, of course, always depending on the use case, there will always be a market for that. But then I guess that especially also when you look in the IoT business, the sensors are definitely getting smarter. There is something called TinyML, where usually where you can also deploy machine learning models on really on embedded hardware, like on really not so good. They are not so good in computing or not so powerful in computing. But then again, you can basically do your inference directly on this chip. And this is where I think the market will definitely go. But apart from that, with the when you use just a normal or like another IP camera, you can actually, when you do a snapshot or when you do with RTSP, you need to do then your own snapshot. Then you can send this to Amazon Recognition, to Azure, Google Vision API. So this would be indeed possible for the snapshot API. So we have just an API where you click and you have the snapshot there. I don't think for other cameras, maybe with some of them this is possible, but yeah, with RTSP, I guess this could be done then.
Okay, good to know. Flo, thank you so much. We are already a bit over time, but that's no problem.
Sure. Okay.
Thanks for joining us today, and I hope to see you soon again.
Perfect. No, sure. Thanks for having me. And yeah, wish you a nice day, everybody.
Perfect. Thanks. Bye-bye.
Thank you. Bye-bye.
So we are again going into a very short break, just 8 or 9 minutes before we start with our next session. Very interesting, especially if you are, if you want to join the machine learning projects, industries, and so on. We will talk about how to get started with machine learning. So stay tuned, grab a coffee, and see you in a couple of minutes again.
Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model. Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model.
Welcome back, everyone, to our third session of today. We are going to learn about how to get actually started with machine learning. And I'm very happy that we will learn this from Waldherr. She is only 19 years of age, but she already holds a bachelor degree in computer science from the Technical University of Dublin. She has been part of some very cool programs at the MIT, CERN, NASA, and IBM. She's researching on quantum computing, and she's also studying molecular biology. So quite impressive. Unfortunately, she cannot join us live, but she sent us a pre-recorded talk that she did for us, and she will be very happy to answer your questions afterwards. So let's see what she has to tell us.
Hello, everybody. This is an introduction to machine learning, and I will start with some biochemistry. So this is a neuron, and I got the task to dissect a mouse today, which is a very tough task to ask a vegetarian to do. But it was actually quite interesting in the end, also a little bit scary, but we got to dissect the brain. And it was the first time I really saw how tiny an organ can be that has such enormous power as driving how we think, how we feel, and how we live our life. And this is truly amazing how it works, and we have little clue how it does. And this is what I want to start with, the history of machine learning. The history of machine learning actually started by people thinking about and wondering how our brain works and how we behave as humans. And soon we found out that there are these neurons and that they together actually fire in some case with like electrical circuits. So we could build electrical circuit models that model our brain so we could do research better on it. But more and more people saw that there's actually kind of a power behind it, not only trying to organize circuits in a way that our brain works, but organizing computers or making machines learn in a way that we do, so that we could make tasks more easily available to automation. And Turing asks, can machines think? Because logic and the logic of neurons is actually a little bit like intriguingly similar. And so it came that we tried to make algorithms that look a little bit like decision trees and that could do cool tasks like playing chess quite well. Or also we could try to model a single neuron by putting in some input functions into one function and applying different activations so that they put out something interesting. So from input, we could do calculations to get to an output or to fire a signal. And more in 1967, we got the snake algorithm, and then we got backpropagation, which is very interesting for a lot of recent tasks. And so the whole family of networks and machine learning algorithms that could try to implement functions that work similar to our cognition became known in this world. But besides all these diverse architectures, we also need one thing to train machines, and this is data. So one hallmark was definitely when in 2009, ImageNet was produced and brought to the public. ImageNet is kind of a large collection of pictures from everyday objects, like a dataset full of images that you can use to train different models. And open data is very important. The more data you have, the better models you can build, especially when you use deep learning. And in 2012, AlexNet was one of the deep learning frameworks that finally brought really broad recognition to the field of AI and machine learning. Because by using deep learning backpropagation and GPUs, which is accelerating the learning process, and this AlexNet was one of the top performers in an ImageNet competition, using this ImageNet dataset to predict amazing tasks. And from then on, industry was very interested in machine learning, and especially companies like Google, Amazon, etc. joined. And we not only got good in applying it to industry, especially for recommendation algorithms, but we also got good in playing games. For example, in 2016, and the machines got very good in playing AlphaGo with reinforcement learning. And then in 2020, we were also good in doing research. So we now have AlphaFold 2, which is an algorithm that helps to speed up tasks in the laboratory that would take years, so they can do them from your couch. But enough of the history. You see, it's a very diverse field, and I could never cover all the topics. The thing that I want to talk about is specifically machine learning, but what is it actually? So one of the best definitions that I found was that machine learning is embedded in artificial intelligence, where artificial intelligence is the whole scope that we humans try to make machines act in tasks that humans do as well. But there's also robotics included, as well as sensor technology. So artificial intelligence is like the whole human behavioral scope, while machine learning is more of the cognition task, like how can we use data to learn specific tasks and not how to execute them, which would be part of artificial intelligence, but not specifically machine learning. And then deep learning is another subfield of it, where we specifically try to use the brain function, like the brain structure, to make algorithms work. And one of the definitions behind machine learning is that machine learning algorithms use statistics to find patterns in data. So in the end, what we do is we have some data input that we collect in this world, then we put it into our model that we choose, and then with statistic optimization, we try to model a function that has the minimum loss for our tasks, and then we have a trained model with the best and optimal function to produce predictions for us with new input. Which model you use depends on the task that you want to do and the statistical method that you want to apply. In general, we can look at two specific, like, rough categories. For one category, we have like data there which has something in common. So there's one trend that you want to figure out and then use. And often this is kind of something linear, something that you could plot, and we often call this linear regression. Normally, in such a way, you want to put in one input value and get value in a range, in a specific range, often a numerical value. Then we call this regression. And on the other hand, we often have a data set where we have different attributes, like they're different factors, they're differing in specific ways. And then we want our machine to learn how to differentiate those things, not how to find a common trend and then use it, but how to find a cutoff and then use this. And then we often use logistic regression. So regression tries to predict a numeric value on a kind of homogeneous scope of data and also of outputs. And logistic regression tries to find the class separation between different classes. So we have regression on one hand, numeric value, and classification, which predicts the correct class in the end. Here are two examples. So we can have some input, like a random set of numbers, and in regression, we would get a specific output. On the other hand, we have the same input, the same features, but we get a class as an output, which is a little bit different. And depending on which model and statistic you want to use, you can either try to do clustering. So if you try to find clusters with similar characteristics in your dataset, or you could use support vector machines. We not try to find the clusters, but we find the boundaries, the lines or the planes, the hyperplanes in between your subgroups, and optimize those boundaries. Or you could use decision trees, where you have this whole data set, and then your algorithm tries to find the exact right questions to split the data set into smaller data sets that go into more smaller and more detailed questions. So in the end, you come out with your optimal solution with your most correct answer. And by pooling a lot of decision trees together, you get to a random forest. And this is what I want to show you today. We want to make a random forest to predict CO2 emissions for a car. So CO2 emissions, numeric value, we use regression not classification, and we use a random forest with this scikit-learn library, which is a very cool Python library that also enables you to use a lot of functions without defining lots of math prior to that. And just let me switch the screen for 1 second. So it should be here. Okay. So what we see here is that we have our dataset, which I got from Kaggle. Kaggle is a very cool website where you can download a lot of datasets and also see competitions that are held on machine learning topics. The tiny machine learning from disaster is very interesting, and house prices is a very interesting regression part. Yeah, a lot of things that are very cool. Okay, but let's get back here. And what we now try to do is to code along something. I also prepared stuff, so I don't want to annoy you just with typing out things. So for example, importing packages is something that we can do together where I don't need to put and type out the code. Okay, what I now do is I download the dataset from a CSV file. So I will try now to also give the CSV file and load it up into our data frame. So data frames, pandas data frame, it's a fancy way of saying cool tabular data that you can work with easily. So I want to read it out, and this is my file path, if I'm correct. Okay, so the dataset is from Canada, and now I try to find out if there's any corrupt data in there, because corrupt data will be bad for our algorithm. So I just ask my data frame if there are any empty entries in any columns, and let it put out the answer for me. Okay, let's see if this works. Okay, no, there's nothing empty. As like it is empty, but we don't have any answer back, so everything should be fine. Now we can look at our data. So let's see how many entries we do have. Okay, so we have 7,000 entries with 12 columns, and each column gives us specific details and information about our cars. So let's see which different columns we have. Oops, this is the name, and this is the function. Okay, so we have the car make, the car model, the vehicle class, etc. Let's see. Okay, so here we have make, model, vehicle class, engine, cylinder, etc. And here in the end, we have the value that we want to use as a training reference, like this is what we want to predict. So we want to get to as close as possible to this CO2 emissions by using these feature data as input. Okay, and also a cool function is describe. So you can let the pandas data frame calculate statistics prior to your stuff. But keep care, sometimes those characteristics and those statistics are not useful. For example, sometimes you have columns in there where numerical statistical data is not really useful. Okay, now what we need to do is we need to separate our input from the CO2 emission label. So the things that we use as input, as information, is called a feature, and the thing that we use as output reference, like as a correction, is a label. So I will split it into our label. And then I will also give away the label here. So from the features, I will drop our labels. And what I then need to do is I need to change all the words into numbers. So we use statistics, and normally statistics don't work with words. So what I am trying to do is I try to use one-hot encoding, which I have with this Weichbrodt, and then we can see that all our car names and model names will be converted into different column names. And yes and no, 0 or 1 answers will be given instead of word entries for further processing. Okay, let's have a look how it looks now. Oops, no, this was not good. We want to code, not markdown. Okay, so CO2 TF features, and we again print the head. Okay, let's see. So we have, for example, in the beginning we had our let's put it here. So we had our make, for example, here, and the model, which were not word or not numerical values. And now the getDummies command transformed everything into a question. So is it an Acura? Yes. So it's a 1. It's not an Alfa Romeo, so it's a 0. But of course, you see that it spans out our much more columns now. So in total, we have now 2,000 columns, while in the beginning, we had much less, right? So we only had 12 or something like that. And this is very hard on training. So what I will try to do is I will cut down at least on the car name, because the car name is probably the most diverse words that are in there. So what I will try to do now is the same thing, but I will drop the model on my axis 1, right? And then again, I will convert it into a number frame, and I will get my head. Okay, nice. So we see that we cut down from 2,000 columns to 96 columns. So we cut down from a lot of different cars to a data set where the car name is not very important. I don't think the car name is an important predictor for CO2, so this should be a fine transition. Okay, good. And then we just need to save all these features that we now have into a list so we can use it later for plotting some fun stuff. Okay, and now we have this whole data, and we first need to give the model something for training, and then put a little bit back that we need for testing afterwards. If we would give all the data in the training round, then it would already know the test answers by heart. Okay, so we need to do for an 80-20 split between those two things. And we can do it by importing, you can do it manually, or you can just import a function from scikit-learn. And then we need to split the test features and the train features and the test features. So this is our X values, and then the train labels and the test labels, which would be our Y values. And with the function, train, test, and split. And then we give it our data frame, and we give it our labels, and then we give it the size of our test, which is said would be 20%, right? And I also include a random state so that we have a reproducible Python notebook here. Okay, nice. And then we can train our model. And this is the really fun thing. At the moment, you can learn so much by just playing around with a lot of algorithms, and you don't need to do so much math at the moment, because they're very cool modules. Just play around, try different models, try what works, and then find out why it could work for something or why it couldn't. So learning by doing and learning by playing is one of the fun tasks in machine learning, and it's also how I learned it, because if you do a lot of chemistry, you are not always best at math. So okay, now for this values here, I put in some hyperparameters. So this is just things that describe my model. For example, an estimator is how many decision trees I put together in my random forest. Then max depth is how deep I want my decision trees to run. And they say, okay, 5 questions is good. They could ask 5 questions in series, but then they should stop, right? And then again, I put in a random state. 42 is nice. And that should be fine. Okay, and now I call the fit function, and the fit function trains my random forest. So I give it the train features, and I give it the train labels, and we train, and it should work. Nice. And now I see all these parameters, hyperparameters of my model, and you could use it to, for example, you could try to play around with this hyperparameter. So would you play with less trees, with more trees? But I will not play with it around at the moment, because it would be a little time intense. What we might try to do is to make predictions. So from the beginning, those are the labels that we saved. The test labels are our accurate values. So those are the things that we want to predict. Give me 1 second. Nope, not markdown. We need code again. So this will be the first 10 things that we want to predict. And those are the values of CO2. And then we will make a prediction call. So this is our predictions from our random forest, that we just trained above here. Test features. Okay, and now we can print our predictions. So print our predictions, the first 10 again, because we've made probably a lot more, and we round. So yeah, maybe this works. Predictions, probably, yes. Okay, and you see that they are some kind of similar. So we have, for example, 253 and we have 247, quite close. Yeah, so all of those are actually quite close. And now we can try to give really cool numerics and put out how the accuracy is, etc. I just copied this because this is just some kind of graph, and we see accuracy is about 98%, which is a very good value. But don't always rely just on accuracy scores. You also need to test if this model really works in the environment you want to use it. So, for example, if it's run in the lab, but not in the real world, then your data is screwed. Look at this. Okay, so now we can try to find out what features were very important. So is the car name the car brand important, or is, I don't know, what is the most important thing? And we see the fuel combustion combined over different environments, for example, road, city, etc., is very important. So, for example, 8%. And the engine size is also kind of important, but much, much less. And the fuel combustion city is also important, a little bit, but we see only 1%. So the fuel consumption is the major part on CO2 machines. And then sometimes it is nice to visualize what you're actually doing with all this code. Okay, so what I now try to show you is that we can put out an image of a random forest. I just need to change here the screen again. 1 second. Yeah. So this is the tree that I just printed. So at the beginning, we have our whole data set, and it learned that if the fuel consumption combustion in liters per 100 kilometers is smaller or equal to 10.96, it can go this way, and then otherwise it can go the other way. And you see it's samples down, samples down, samples down. And here at the end, it gets closer to predicting values, right? So you see here, there's different values. For example, this would be the value it could predict here or here. So it starts with 250 and then it fine grains down to less values here or to higher values on the other hand by asking the different questions. Okay, so let's go back to our presentation. This was the coding part, but how does it work? Like, how do the machines work? First, we have the training step, and this is where machines learn. So this is the model training. This is where the machines learn. We need to collect data and feed that to an unread model. Then we get our machine learning model and we can refine it. This is where we use the validation data with the test data, right? That's just what we did. And then in the end, we have the model application set, and then we use data. So we can pass new data to the model and get prediction. So we have a training step, a validation step, and then the application step. And we should not mix it up. And the training is where the model learns. So this is the part which we focus on now. So let's see, we have data input and we train with statistics, but we not only train with statistics, but also actually with analysis. So with the math field of analysis. Analysis, I think it's analysis. Okay. See, this would be how we do linear regression with a specific model, which is called gradient descent. So we could just try to plot one line. Okay, so we have one line, and you see there's a big discrepancy between our data points and our line. So the loss of this slope is very high. So we have the line parameters, and for this specific line parameter combination, it's a high loss. So then we can try another line, for example, this one. And we see we have higher line parameter values, but the loss is still quite high. Okay, so we get another point here. And we see it's not really optimal. And then we can try to wiggle around with this line in steps. So try different values, go up and down, and then fine grain and fine tune it to one value in the middle. And then we see, okay, we could plot such a loss function in the end. And we see there would be a minimum in this case. Yeah, this looks two-dimensional, but we can have it with 3 dimensions or multi-dimensions, depending on how complex your function is. And then you just look for the optimum. And this is the minimum loss. And this method is called gradient descent and is very helpful. On the other hand, we also have deep learning. And deep learning is focusing more, as I mentioned, not only on the tasks where we could learn how to do tasks, but also on the structure of how to learn the task. So we try to model neurons. So we have neurons and connections in between them. And those connections are actually kind of numeric values. They can be of higher value, so higher weight, higher importance, or of lower value. And in the beginning, we just start with some values. And then by feeding in input data and learning if the output is correct or not, we can back propagate it. So it's like we put in data, look at the output. If the output is good, we strengthen the modes that we just used. And if it's bad, we weaken the connections that we used. And by this, we tune these weights and have a trained model with some strong and some weak connections. This is called backpropagation. And then we can take our data input, feed it into our model. Then our model will predict something depending on the weights that it is trained on. And one of the output nodes will be higher. So one neuron will fire much higher than the others. So there will be a higher probability output. Like, for example, this is the output. I don't know what it is. It's class 2 or whatever, right? And so this is our prediction. And different architectures can provide different strength or weakness. The first one that was provided or like discovered was the artificial neural network or build. So we have one layer in between. So we have the input neurons, then we have one hidden layer of neurons, then we have the output layer of neurons. And you see all of them are connected, but it's just one layer. And the state of a deep neural network is now if we put multiple of these hidden layers in between the input and the output layer. And all of these nodes, like the neurons, are matrices, also the weights are matrices, and everything here is linear algebra, like how we can multiply these things and how we could use a lot of data, which is very cool and interesting, but I'm not the best, or like still trying to figure everything out. But linear algebra is in general very cool if you do computer science, so maybe have a look at that. Okay, and in between the different layers, and we can also use activation functions, because in biology, for example, if a neuron is like, if there's a nerve impulse coming to a neuron, it not necessarily means that it fires, right? Only if there's high enough input, it fires. And we also try to implement this with different activation functions in neural network, because then we can put in not only linear dependencies, but also nonlinear dependencies, which makes the whole thing a little bit more, or like less predictable, but more naturally in learning abstract tasks and learning itself, things that we could not use statistics for. Okay, so let's just see where my cursor is here. And one very interesting one are the resonant models, which are convolutional neural networks. So convolution means that we have layers with a lot of output, and each layer feeds on the other layer by pouring in specific attributes from different parts. And so it condenses everything a little bit down. And those convolutional neural networks are very good at getting pixel input, pushing out features from there, pulling those into the network, and then calculating something on it and predicting a class. So convolutional neural networks are very good with image recognition. This is where AI or deep learning in general was very good in the beginning, and now there are also other methods. For example, we have other methods, the transformer method, like recurrent neural networks, where kind of some of the training is fed into, like the neurons not only put out input to the next one, but also feedback while they are working. And this is important when you try to understand sentences or words, because there also every word is connected to the next word. So you need to get some information back to all the other actors that you give this kind of coherent feeling of one sentence with only single words. And transformer models are a mix of different parts, which are very, very cool. And there are also this bird model. So there's all bird. They're very cool for different things of birds. They're very good with language tasks at the moment, just to have heard of it. And we also have autoencoders, which is not for one specific task, but rather an architecture. We have input neurons, then you have some hidden neurons in the middle, which are kind of condensing down the most vital information, and then you try to scale up from there again. And they prove very successful transformations in some specific tasks. But I skipped this slide. These are the two main frameworks that are used for deep learning, which is PyTorch and TensorFlow. There's also Keras, but PyTorch is by Facebook and often used in academia, while TensorFlow is by Google and a little bit preferred for applications and production. And I want to show you really quickly how one framework which you can use fast on your laptop is built on PyTorch, and this framework is called FastAI. So let's try this with the ResNet model, this model. Give me 1 second, I just need to switch screens again. Let's see. 1 second. I'm sorry. Need to find the correct screens here. And switching around and switching here. So we have this and we have this. So what I try to do, a classification this kind, not last time we predicted a value, right? A numerical value, so we did a regression task. This time we try to find a class of an image, and I try to look at graphic data sets. What I did do was I got on Google, and then I put in some traffic, for example, I don't know, pedestrian as a search, and then we can go to the images. The fun thing is, if you now download this site, you get not only the HTML data, but also if you scroll down, especially like this, and you download again, which is very fun. Do it only at home. Don't use this always for model link because, of course, privacy issues, etc. And then you go into the download folder, which takes 1 second again because I need to switch screens. You see that not only was downloaded the Google folder here, but we also got the whole images. And these images are kind of noisy data. This is just Google data, so it's not perfect. And you can use now to look at, is your model perfect? Or how good would your model work with real data? Because if you clean all the data, then maybe your users won't input only clean data as you would. That's why it's cool to also work with uncleaned data and just look at performances. And you see, if I go back to my notebook now, that here I did everything. I also did the validation and training split on 80-20. I cut down the size, I loaded the data set for training, and I trained a little bit. And we see that we actually have an error rate of about 25%, which is much worse than the 2% that we had for the decision tree, right? We could also try to find this loss versus learning rate, which is a little bit like the plot I showed you before with the learning curve, a little bit not the same. Then we can save model. But we see that what especially is interesting, we can have confusion matrices. So in my case, the biggest problem was that I used intersection as a category as well as junction. And we know that those things are actually kind of pseudonyms. So this was very hard for the model to differentiate, and that is why I get very high loss here. Ideally, if you use confusion matrix as a plot to find out where your model is good, it should only be high in the diagonal and everything else should be not activated, because everything here is an error. Only the diagonal ones are the correct ones, right? So this is a very interesting thing, yeah, but I won't go too much into this. Also, segmentation is a very interesting word. In segmentation is when you try to not only classify an image, for example, not only say, okay, this is a pedestrian, or this is a tree, or this is a junction, but what you do is you try to find out where in the car, like where is the sidewalk, where is the road, where is the building. And this is how, for example, medical devices, like medical imaging tries to segment, like, could this be a tumor or could this be the lung tissue? Or cars look like, where could I go? Where could I drive? Where would it be safe? Okay, don't have everything like too much time left. Let's go back to our slides. I only have some last fun things to do. okay, this we had, this we had, this we had, this we had. So we have convolutional neural networks for image, we have recurrent neural networks, long and short-term memory for language, and we have autoencoders with specific architectures. And those are very good sites where you can learn. So Google offers a free machine learning crash course with explanation, for example, what is a label? This is what we did. What is a feature? Also giving you steps into TensorFlow with interesting examples, and also showing you in one of the first labs, for example, how a TensorFlow model really tries to draw out the edges of images and works with the different convolutional tasks. And then also Stanford offers a course in Coursera, which is for free, and you can learn a lot of very good math there. And those math introductions are very, very interesting, and I'm a very interesting guy and very cool things. So highly recommended, try it out. Yeah. And the thing that I want to leave you with is what could be problems, what pretty cool things that you encounter on your journey. So problems could be, on one hand, that you overfit your model. So in the end, the model that you use for your data is too intelligent. So it tries to learn every image by heart. So it kind of outsmarts the data. So the model is too complex. So the data set is too small. The model just overachieves in the end, and is not general anymore. So it's very good for your specific data, but not for general data. So try to find a less complex model or a more diverse data set. On the other hand, if you go the other way, you have an underfitting model. So the model cannot meet your standards. The model is too simple to grasp what your data actually means. And then you need to figure out, is the model correct, or is my data set even clean enough? And if the dataset is not clean, there could also be another issue. For example, it works well on your laptop, but it works bad in the environment. Then you need to look if there's bias in your training data, or is there something that I'm missing, or is the real world totally different than the model I trained for? Yeah, this is very interesting. And especially if you get better accuracy, look at your data, look at the data quality, and also think again, is this model the correct one? The most important thing with machine learning and artificial intelligence and deep learning in general, you don't always need a neural network for everything. Like, don't overkill it and use good data. That's the best part. Like, go the simple path first, learn with it, and then scale up, because also, in the end, most models boil down to statistics or probability in some cases. And this is not really a guarantee as if you did hardcore code programming. Of course, bugs are always an issue, but still, like, good data, no overkills, better, good standards, and safety sometimes is also nice. And on the other hand, if you want to play around as much as you like. There are so many cool libraries to do that. Outside the box, one cool thing that you could play around is TensorFlow Quantum. I just recently got into it, and it's very interesting because it tries to support, like, their machine learning is used to support quantum computers that can make errors. So at the moment, we have quantum computers that are very noisy and are not very good in keeping the physical state for a long time. So what TensorFlow Quantum tries to do is to use machine learning to find out where optimal quantum algorithms lie that can be operated most securely and most long-term safely on a quantum chip. So we often rotate them with specific angles, and some rotations are better than other ones. So we can put in a quantum algorithm or a quantum-like circuit, and then use quantum machine learning to kind of figure out which rotations are best and where we can tweak our circuit to make it best applicable to nowadays quantum computers. Another thing that is very cool is AlphaFold that I told you before. AlphaFold is amazing because you can put in a random ledger wiggly, which is an amino acid sequence, so something that is directly transcribed from your DNA, and then it tries to fold this letter sequence into a 3D shaped model of atoms. And in biology, shape is everything. So if you have a protein, the amino acids in there are important, the chemical structure of the amino acids is important, but it's also very important how it's oriented in a 3D shape. And this is what takes amazing amounts of times in the laboratory, because you need to make crystal stuff, and then you need to do X-ray diffraction, etc., to really find the position of each atom. And by putting a large amount of time, data, and also cool algorithms, AlphaFold now even put out a protein structure database where they try to make most things available to you on your couch. Especially, they put everything on GitHub. So if I share my screen one last time, What I just did today is I took one from protein database, a sequence on potassium channels, and potassium is a very interesting ion used in your brain to think, because not everything in your brain is electric. Most of the things in your brain actually are ions moving around, not electrons moving around. And you see those are subunits. So for example, this is one subunit, the blue one here, the blue one there. And I put this amino acid sequence of this one into AlphaFold and just let it run. So I just need to push it in here. They made a very good application. I get a lot of stuff that I don't really understand yet, but I get that output here. So this is like the 3D model shape that I get from my wiggly random letter thing. And this is just a machine trying to fold it. So I give it this thing, and it gives me this stuff here. And if I look at this subpart and look at this subpart, there is kind of some similarity. It's not perfect at the moment, especially for these proteins, because it's very hard if you have monomers, like if you have polymers. So if you have monomers, it's easier, but if you have a whole structure where different are aligned, it's harder. But it's very cool. Like we try to get closer and closer, and it's very interesting. Okay, also another thing where you can use AI is if you, for example, struggle with words. While I was looking at talking through the talk beforehand, I did not find the word for read a whole bar. Like I did not know what repeatable meant. So I can just go here into Sheets and put in Google Translate. Google Translate this from auto detection into English, and now I have repeatable. So yeah, I used the random seeds, like the random states, to make repeatable Python scripts. Okay, just random talk here. Going back to the last slides before I bore you immensely. So this was AlphaFold. This is the protein sequence. Oh no. And yeah, this is like, we don't know yet how our brain works. We also don't know how machines work, but we know that some stuff works. And yeah, we have the ability to ask more questions if we use machine learning to just ask them, because we have more data, we have a higher power to do something with data now, because machines can look through data much faster than we do, so we can ask new questions. And the last thing that I also found today, which is very cool, what I haven't shown it to you today, is so there is in Japan an AI person who decided to make an AI for pastry, because in Japan people want pastry in the shop in various different shapes and kinds. So one bakery can have multiple hundred, like even up to 100 different pastries, but people don't want any barcode or any plastic on it. So each cashier needs to know each code and everything by heart when typing in the whole thing to sum up the cost or the purchase. And that's why somebody decided to program an AI to make it easy for the cashiers to just scan the thing, and then the cost is automatically added to the bill of the customer. And yeah, now it was used to look like it was abstracted to detect images of cancer cells. Like you give it a microscope slide of different cells, and from knowing the specific shapes of bakery, it now gets much easier things with looking at specific shapes of cells, and also looking at damaged cells, looking at cancer cells. And it's actually very good doing that. And this is not really done even with deep learning, but more with machine learning, with the more standard models, with the more statistic models. So a little bit more hard coding, a little bit less data, but this makes it in some cases more secure. So there's so much out to explore, so much out here to learn. So we need just to ask new questions, get explorative. And yeah, if you have any questions, I'm not live here today. I'm very sorry, but hit me up and ask, and build a community, get the questions together, help yourself out. And I'm curious to get an update on what happened today. So thank you all for being here with me today. Thank you all for the training, and I hope I didn't bore you with too much programming. Otherwise, give me some feedback, give me comments, and I will try to improve, because machine learning is not my best discipline, but it's very interesting to play around. Okay, so have a great day, and it was really nice talking to you. Bye.
Hey, so I think that was a quite interesting overview about what's possible with machine learning and how you can get started with it. So if you have any question to Alex, just drop us a line to hello@wearedevelopers.com and we will happy to provide you with the answer from her, or just ping her directly on social media. So with that, we are going in our last very short break and we'll come back in 15 minutes with our last session about deep learning for drug discovery. Stay tuned and see you in 15 minutes.
Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now. Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model.
Hey, welcome back everyone to our last session of today. I am here with Noah, who is a mathematician and has multiple years of experience in deploying machine learning solutions, and he's working on a very interesting project right now. Hi, Noah.
Hi, Seat. Thanks for having me.
Thanks for joining. Noah, what will we learn from you today?
Yeah, we're going to learn how we can leverage machine learning, more specifically geometric deep learning pipelines, to generate new drugs and combat some of serious diseases that we still haven't solved. And how does that work computationally inside a computer?
Okay, that sounds very interesting and sophisticated. So Noah, I would say, you can share your screen and start right away. Have fun. See you later.
Thanks. Cool. Yeah. So it's a year 2021, and we are still unable to treat Alzheimer's, Parkinson's, Huntington's, and many other diseases. The question becomes, why is that? Well, one reason is that 80% of all the possible proteins, pathogenic proteins that are associated with certain diseases, are simply undruggable. What this means is that if we look at it from just a high-level perspective and without much biotechnology or life sciences experience, every disease has a protein that's associated with it, and there are multiple ways we can combat this disease. But talking specifically about this protein that's associated, we can either inhibit it, and less than 20% are inhibitable, or we can try to degrade this protein. And exactly this technology of degradation is what we are trying to automate with AI. But coming back shortly on the possible therapeutic solutions or interventions in this regard, is we have the DNA approach, CRISPR-Cas9, where we can edit out the gene, the RNA intervention approach, RNA interference, or the inhibition of the protein that's associated with the disease. Now, the problem with the first two is that they are late by design. So meaning that this pathogenic protein has already, the disease that is associated with the pathogenic protein is already developed. We are too late. And inhibition, as we saw, doesn't work in most of the cases, meaning we can only inhibit certain types of proteins and molecules. That's where the degrader technology comes. And this degrader technology is nothing new. It has been around for around 20 years plus. It has been researched, and there has been a lot of papers around it, and it has experienced a winter in itself where for the, let's say, last 15 years, there hasn't been much research, but then it has sparked interest in the last years where some of the new papers came out. But the basic gist of it is that it's very slow and expensive to do in the laboratory, meaning not to simulate it. And then the question becomes, what can you do to speed this up? And this degrader, as we said, short for targeted protein degradation as a biotechnology, it shifts the paradigm from inhibition to degradation, where we no longer fight the symptoms, but eliminate the cause of disease. And these two pictures, I'm going to elaborate a little bit on them. Again, no biotechnology experience is needed. We are just going to see what does this mean from the computational or the ML point of view. So if you look at the left picture, you see the E3 or the pink molecule, which is a E3 ligase. And then you see the yellow one, the protein of interest, and they need to be connected together. In the moment when this connection happens, which these proteins are just molecules and they need to connect together, when this happens, then the ubiquity, meaning the proteasomal degradation happens. This degradation then creates the protein of interest, as we see in the middle picture, and we can eliminate the cause of disease. Now, coming back to the right, the farmost right picture, in order to trigger this process of degradation, we first need to connect these two molecules, meaning these two proteins, E3 ligase and protein of interest. In order to do that, we need to find a couple of more puzzles, to call them. Again, molecules, but they come from different families. They are smaller and they have different properties. The first of them is the E3 ligase ligand. That's the first part. Then the linker, that's the bridge in between these two molecules, and then the protein of interest target ligand. Now, as you can see, what this basically comes to is that we are trying to find the best interaction between 5 molecules. Now, the trick here is it's not just defined across one dimension, meaning we have to make sure that they are geometrically right together, meaning they interact, but we also have to make sure that physical, chemical, biological requirements are embedded into the data and that they are also satisfied when this sort of interaction happens. This is absolutely essential because we cannot attack this problem from a simple combinatorics standpoint of view, meaning we have 10 to the 60th of the possible molecules out there. That's the space, huge. But we cannot just try to, brute force try out whether some of the combinations work or not. But rather we have to smartly insert requirements into the data, quantify this, and when we have embedded this data, then we can proceed to determine the interaction. Now, this is very a high-level overview of what's required from the biotechnology standpoint of view, and we're going to go into the details of the machine learning and how the geometric representation helps. And I already touched upon this. How do we translate this to the AI point, right? We have the data. The data is very tricky because, as I said, we are talking about a huge space that needs to be parsed, 10 to the 60th of the possible molecules. But then we need not only a lot of data to be parsed, but we also need smart representations. And representation means we need to think about what's a native way to represent molecules, atoms, and their interactions, right? And I have a dedicated slide in the discussion for this, but basically non-Euclidean data is, or more specifically graph data, is very available or its native way to represent molecules. The reason is simple. When you think about on a nature side of view, how do molecules and atoms interact together, then it's basically the same ways the graphs are represented. You have nodes and edges, and there are multiple possible edges that represent complex relationships between intermolecular and interatomic states. And you want all these complexities to be embedded into your data. And finally, we have the data, we have represented it the way we need to represent it. And then the question becomes, what are the smart algorithms, not only from the graph neural networks side of view, but also from the parsing of this data, right? So we need active learning, more specifically Bayesian optimization, to help us navigate the huge space of 10 to the 60th of molecules. And at the same time, we need fast geometric deep learning algorithms that are available to make inference in seconds time, right? Because at the end of the day, this is not a research project. This is a solution that we are offering, and it's very important that we deliver real-time inference. And coming back to the geometric representation, graph representation of the molecules, and the importance of this new emerging topic called geometric deep learning. I think it has really in the recent years been researched a lot, and there has been seminal papers describing what this does and depicting the theory behind it. And I think we will see more and more companies using this because non-Euclidean data is everywhere. If we take just one example, a super simple example, and I think everyone that has some contact with computer vision or standard computer vision algorithms will note that if we were to train not very sophisticated computer vision algorithm with some convolutional layers, more likely than not, the first cat will be grouped with a dog and not with the second picture, meaning the white cat. The reason for this is that in the standard approaches, what's basically happening is if, as I said, the convolutional layers are not sophisticated enough, what's happening is that what this convolutional operator is interested is only the pixel to pixel comparison. But obviously, this is not sufficient because we have much more intricacies and complexities involved that constitute a cat or a dog. So just because the two objects are black and look like an animal, that doesn't mean they belong to the same class. Obviously, there is hereditary, there is the genetic, there is so many different intricacies and relationships that also need to be encoded and represented into data, which we cannot do with the Euclidean representation. And Euclidean, let's say the Euclidean main assumption is that 2 points in a data space are close together if they can be connected with a straight line. And this is obviously not true because, as I said, there's much more intricacies in being close together, meaning being similar to each other, than just standing close because of the pixels or being close in a certain space. And exactly this kind of complexities we need to represent, and that's where the geometric deep learning comes. What obviously one tricky part that we are going to see is that obviously we cannot represent them. Relations are also there, but then the question becomes convolutions, meaning the standard operators or the standard machine learning paradigms that we could apply on Euclidean data are no longer valid. And I'm going to give just one example. So in order to apply the convolutional operator, just speaking strictly from the computer vision sense, you need to have some sort of sense of up, down, left, right. You need to move your convolutional operator. Obviously, you're moving the convolutional operator in your tensor that represents the object at hand. But the problem is, when we are talking about graphs, there is no concept, or there is no explicit concept of direction. Right? We are in this graph space, and what constitutes up? There is no direct representation of up, down, left. So what's really important, and what researchers have been able to achieve in the last couple of years more extensively, is to generalize these sorts of operations so that they are also capable of applying them on graphs. And this is super important, because when we are talking about life science applications, like, for example, generating new drugs, and you are representing your data as graphs, then obviously we need to operate on these representations. And not only is the research, let's say theoretical research, so advanced, there's now a lot of libraries that offer using some of these methodologies off the shelf. So for example, PyTorch Geometric, which is independently developed from PyTorch, but it's obviously based upon that, allows you to now not re-implement or reinvent the wheel regarding these generalized convolution operations, but you can use it off the shelf and then apply it on your molecular and atomic data. And now maybe to come to concrete implementation of our pipeline from a high level point of view, what we are actually doing. So if you remember, the task at hand from a very high level point of view was, you have 5 elements, 5 molecules, and you want to determine how are they interacting optimally. Now, one can imagine, and I will just underline this again because it's very important, it's not only about geometric interaction. We have to make sure that all sorts of different requirements, for example, chemical, physical, biological, are also satisfied, and we are optimizing also based on these properties. So coming back to the problem, as you can see in the step 1, what we are primarily operating upon are the 3D structures of the molecules involved. This is important when we talk about proteins, and I guess very relevant for our conference now. We are talking about machine learning. Everybody saw what AlphaFold from the DeepMind managed, and what they basically managed to do is the problem of protein folding, which takes the 2D structure, that's the, let's say, the first line in our step 1, and then converts it to a 3D structure. And these 3D structures were not, for actually majority of the proteins, were not available, or what were not known and researched. But now with the end-to-end model, we can infer them. And once we know these 3D structures, there's a lot of possible applications in life sciences that allow us to research better drugs, research better molecules, and find a lot of applications. Now, not only are we using 3D information that is obviously then embedded into graphs, so it doesn't stay in the 3D object, we are also using chemical and geometric, meaning embedding all the requirements from chemistry, biology, and physics. And these embeddings of requirements are actually constituted or are entailed in these graphs. So now you have quantified exactly what you need to be fulfilled and what needs to be taken into regard when you build your model. And then this step number 2, you're reading protein ligand interaction. What this basically means is, you remember we have 5 molecules: protein, ligand, the bridge, linker, then again ligand, and then again protein. These are these 5 molecules. And initially, what we are essentially doing here in the step 2 is the breaking our problem down to individual components. So instead of trying to with combinatorics, or instead of trying to solve all 5 interactions at the same time, what we are actually trying to do is to first determine whether interactions on only 2 pairs of molecules are happening, meaning on protein ligand, and then again on the second pair of the protein and ligand. And this protein ligand interaction is for the people that have bioinformatics or biochemistry background, is pretty researched. I mean, it has been already more or less solved from a standard or classical point of view. But what has not been solved, and it has been only researched in a couple of months, is solving it with geometric deep learning. So there has not been many research institutions that have focused themselves on this. And attacking this from the strictly geometric deep learning perspective allows to model much more intricacies between these two elements than attacking it with standard point of view. And exactly this enabler we are seeing, and there are publications, not only we are also making publications on this regard, but there are different institutions that are showing now that this approach to modeling this interaction between proteins and ligands, generally molecules and molecules, is highly more effective than the standard classical ways. And this sort of effectiveness, where you can initially predict with high accuracy what's the interaction between two elements, is very useful, because as you can see, if we are failing in the step number 2 and we are filtering it wrongly, then anything that we do subsequently will be wrong. So after we have tackled the problem number 2, or the column number 2, then I would call it the core module, because the pipeline is constituted of several modules that make the entire solution. Then the core module, as you are reading, constitutes of deep linker generation, deep molecular conformation generation, and then the Bayesian optimization loop. Now, these are maybe a tongue twisters, and there's some confusion, but it's essentially what we are trying to tackle with this pipeline number 3 is, when you have determined that couple of molecules or elements are potentially good to interact with each other, then you need to determine what does this interaction exactly mean. So as you can imagine, two objects, right, in a 3D space, they can interact differently depending on their relative translations and rotations. And not only that, when they interact together, as in the case of the two molecules, they can change the atoms on the surface of their interactions. So what I'm trying to say is that with this step 3, there's a lot of possible, not only combinations of molecules, but also their positions to each other that they can interact with. And as you can imagine, you have the space 10 to the 60th of molecules, and then you have the space of all the potential poses or rotations that they have to each other. So here, it's not possible and it's not feasible to apply raw computation, and we will see afterwards what did we do in regards to this, and how is cloud actually essential to performing any kind of large-scale machine learning computation. But what we have did is we have applied Bayesian optimization loops, where we try to not with brute force, but smartly evaluate every possible rotation and translation of the molecules, and then learn in what direction should we move in order to find the optimal pose between these molecules. The reason why is this important is because we cannot check every corner of this high-dimensional space in order to determine this. We need to make sure that we have a function that we are evaluating, and we are basically parsing the space. As I said, it's not only molecules, but also the poses, parsing this huge dimensional space very smartly. And then when we aggregate the first 3 elements, the first 3 columns or our modules, you get a non-deterministic suggestion, meaning the step 4 or input to the step 4 is not one best ternary complex ternary complex is basically this complex of all the 5 molecules, we don't output only one. It's not deterministic. We output a list of suggestions that are highly probable and that will most likely show the properties that we have optimized for. And then you have a list of 100 molecules that are very promising. And then you apply standard chemoinformatics tools like MDM simulations or density functional theory, etc., to make sure from this physics standpoint of view that this makes sense what we have provided. Because as I said, we are trying to automate something that's very expensive in the lab, but at the same time, we need to make sure, at least computationally with simulations, that this makes sense. And at the end, you get a ternary complex, right? This is the suggested complex that would degrade the pathogenic protein of interest that we have discussed later on, just coming back shortly to this, right? This ternary complex is exactly the right picture where we have determined these 5 molecules. And depending on your choice of protein of interest, pathogenic protein associated with disease, you can target some of the diseases. And we have already moving towards, we have already developed, as I said, we are focusing on Alzheimer's, Huntington's, and Parkinson's degenerative diseases. And we have already in our pipeline a couple of diseases, or better to say, a couple of solutions to these diseases that are moving towards preclinical and clinical trials. So we already have molecules that have shown promise and that we want to further validate computationally and non-computationally in a laboratory that we have set up in Graz. And there we will make sure that these chemicals do what they need to do as we have predicted, and that they, at the end of the day, tackle these serious diseases that we are still dying from. Okay, that was shortly on our pipeline. And then just another expert, not to go into too much detail, this diagram essentially says what I already said with the Bayesian optimization loop. You have all these possible configurations, meaning different poses of molecules to each other. That's depicted in the blue and pink positions of the molecules. And then you're just trying to evaluate, right, what's the best final valid complex, meaning what's the best interaction between these molecules, and you are evaluating this with some sort of function and some sort of fitness function. And there are multiple functions that constitute this. These functions basically entail all of our requirements for this ternary complex. That's PPI fitness, constraint fitness, etc., and you get the combined fitness score. And what's essentially important to take from this is the combined fitness, meaning fitness of all the requirements, is influencing the decisions of what are the next potential examples of the final valid ternary complex. So it's a standard active learning loop with Bayesian optimization, but what's tricky about it is to embed all of these different requirements in this high dimensional space. One interesting module of our solution, as I said, there are all in all over 7 modules that we are using for this solution. And one interesting module is the generative models for molecules. So you can imagine what we are trying to do is not only take existing space of molecules 10 to the 16, we are also trying to generate completely novel molecules that are not available, that we don't know anything about them. And one example of concretely what we are trying to implement is generate a linker, completely novel linkers that constitute and satisfy all the necessary requirements. Very shortly, what is the linker? If you can remember, that's the bridge in between, in the middle, meaning the third molecule that connects these compounds before. So what here is very shortly depicted, what happens is, as input, you get the 3D coordinates of the fragments. These are the ligands that I talked about previously, without the linker. And you want to determine, or better to say, generate de novo molecule that will connect these these two fragments, right? These two molecules, but also at the same time, as we are generating, we are making sure that this new linker is satisfying different graph metrics. So these are toxicity and different pharmacokinetics properties. That's on the one side, that's the left side, and on the right side, which all constitutes fitness, we want to make sure that this molecule, the linker, is also minimizing the energy or the RMST between these molecules. Now, for the minimizing of energy is essential because the lowest energy is what constitutes the best interaction as when we put the molecule in between. And the interesting part is you can basically create these generative models to basically have new molecules that are not available there, and you are essentially playing with atoms and different requirements that atoms entail in order to create these molecules, because as we know, molecules are constituted of atoms. And coming to the point that I mentioned previously, that was also very essential, because without that we couldn't basically do it, is cloud and machine learning are the same. This year, I will go very briefly through it because I don't want to explain the whole architecture, but we needed to basically develop our own architecture on AWS and Azure also as our partners for cloud, in order to use the computing power more efficiently. So as you can imagine, deep learning, very expensive, Bayesian optimization, high dimensionality of space is very expensive. And now with the geometric deep learning, this all explodes. So there's a huge need for GPU instances, parallel clusters, a lot of computing is needed for this to work. And what we needed to do, because off-the-shelf offerings were not enough for us, we needed to optimize it more. We have created a simple solution with, on AWS Cloud, you have the so-called spot instances that are very cheap, but they die if the need or demand is higher somewhere else. So we needed to make sure that these spot instances or the spot fleet is persisting or saving models, checkpoints, and results, as you can see in the middle, to the EBS volumes, and then we are taking snapshots to the S3. So what's happening essentially is we start these spot fleets, and then based on the spot instance that we are running our code, we make sure that after every epoch, we are serializing the model artifacts and the weights, biases, and everything that's associated with the model, so that we don't lose it. If the spot instance goes down, we already serialized that on EBS, and we can just continue our training from that point on. This was very important because you can design the smart algorithms and representations, data, etc., as much as you want, but the computing power will still be needed. So associating that with the cloud from the raw computing standpoint of view, but also from the software standpoint of view, where you think about these different offerings that you have on the cloud. Here, in this case, it's raw computing power, but then talking about something like AWS SageMaker, which allows you to experiment faster and get faster time to market and leverage some of their services there for debugging, for detecting model bias, drift. This has been also very essential because at the end of the day, you're a startup, you have only so much resources that you can invest. And it's important to strategically leverage these services in order to get faster insights and develop faster. And now concluding, what were some of the other AI enablers that we managed to solve or tackle this problem more efficiently? We talked about the data quantity and quality. I mentioned AlphaFold that allowed the 3D structures, but generally there has been a lot of research, a lot of institutions around the world have been publishing not only from the machine learning standpoint of view, but from the biology, chemistry, chemoinformatics, all of these different disciplines that basically then constitute the degrader technology or targeted protein degradation has been very important for us, because as we know, if data is not there, nothing will work, and he who owns the data owns the AI. Then the active learning Bayesian optimization algorithms that we already mentioned, new methods from the geometrical deep learning standpoint of view, but also from chemoinformatics. There has been a lot of research and open source stuff that we have leveraged in order to not reinvent the wheel. But obviously then we needed to use our own custom graph deep learning models and modules that we have already patented solution for. All of these models that I explained before are already submitted a couple of months ago to the patent lawyer, and it's already in place. And then at the end, cloud and computing power was really, really important for us. And this is really not to be decoupled from machine learning. Another thing that I think was essential from company building standpoint of view is, had we have came and said, let's just take 20 computer scientists or 20 data scientists and let's solve this problem, this would not be possible. It was really essential for us to get experts and PhDs from different sorts of backgrounds, from chemistry, biology, physics, mathematicians, and then engineers at the end of the day for us to solve this problem. Because as I said, it doesn't matter what you automate or develop in this field. If it's not validated from the domain experts, then at the end of the day, you will realize that you made a mistake only when you have finished the solution. So it was really essential to have these validation steps in between with different people doing the interdisciplinary work and making sure that these communication points are really available, so that we are certain we are building something that's truly valuable and that's tackling these diseases. And that's it. We are Celeris Therapeutics, and we are making better drugs faster.
Hey Noah, thank you very much for this overview. I think it was interesting even for people who are not that deep into chemistry and all of these disciplines. Maybe a first question from myself. How hard is it to work on such projects where you have really multiple disciplines and, biologists, physicians, experts in chemistry and so on? How hard is it to get, all the input and work on such a project?
Yeah, I think if I were to summarize the hardest, let's call it the hardest part,
or challenging.
That's the most challenging part, right? How do you effectively communicate between all of these different parties and then make hands-on insights that are then transferred to data, transferred to computation, right? Because let's take my background, right? I had experience in computer science, mathematics, right? But before this, I didn't have too much experience in the life sciences, in chemistry, biology. Then the question becomes, how do you make sure that you are really taking the most important information from the experts in these fields, right? And then transferring that. I think one of the core, most important solutions to this question is, what talent are you hiring, right? It's easy to say, but I think it's really essential when you make sure that the people that they're also hiring are not only experts in their own fields, but are curious about other fields and are able to adjust to this, then this communication bridge becomes easier.
Okay. Okay, then let's see what questions do we have from the audience. We have one question regarding the cloud service. So have you considered other clouds, and why did you choose AWS at the end?
So as I said, we are also in Azure partners, so we also work with them. We love some of the services from Azure. We love some of the services from AWS. So definitely, and we are developing cloud agnostic. So we are definitely, not locking in. I think how I like to think about it, especially in our use case, is differentiating the computing power and the software side of the cloud. As I said, there's a super cool solutions out there from the software point of view that you can leverage. And then you also need to be smart about using the raw computing power, because it's not always catered to, running hundreds of GPUs, months on the end. These bills are huge. So we are definitely leveraging different kinds.
Absolutely. Okay, cool. Then we have an interesting question from Alspeter. He or she is asking, when running Bayesian optimization to find the best fit between the two objects, do you also evaluate interaction energy?
Do I also have what?
Do you also evaluate interaction energy?
Yes. Yes,
okay.
This is
short and simple. Yes. Good. Then one question from David. What do you think about Coursera AI for medicine specialization?
I'm not familiar with this course, but I think generally, maybe a little bit philosophical question. If you don't have a specific problem in mind that you want to solve, and the best course in the world won't help. So I think it's always helpful to have a concrete problem you want to solve and then gather that knowledge that you need. But I'm not familiar with Coursera.
Okay. Yeah, but I think that's a good general advice. Like, it's always easier to think about the possibilities if you have something concrete.
Yeah.
Then maybe a short summary also for Marek. Like, how do you use deep learning in this case?
Right. So maybe short summary, right? Or let's say deep learning, geometric deep learning, it doesn't matter, right? The number one use case is predicting the interaction strength. It's a scalar value between two molecules, right? So you take two molecules, we are talking now here protein ligands, but generally you take two molecules, you quantitatively represent them however you want, and then you apply deep learning to predict the scalar value. That's maybe a short sentence.
Okay. Then we have a question from Lily. I think it was kind of in the middle of your presentation when you had these 5 steps. She's asking, why is your approach better than other existing approaches?
Approach to what? To tackling the diseases or tackling because, for example, this degrader technology, targeted protein degradation, we are the pioneers. So we're the first one that started working on this. I'm not even sure if anybody is even working on it, to be honest. It's very niche, right? So as I said, from the biotechnology standpoint of view, there's little companies or research institutions that are researching this, and then especially not trying to automate it from a computational standpoint. So I think why are we the best in this regard is because we're the first and almost nobody is doing it.
Okay, that's good. Noah, as we are coming slowly to an end, is there something else you would like to share with the audience? Or maybe you want to tell us a bit about your team, like how big is it and are you looking for some colleagues? Or
Yeah. So I guess currently I think we have more than 20 full-time employees. We are mostly based on Graz, but we don't have a strict office policy. It depends really on the circumstances. What's maybe important and interesting to note, I already said it as part of the presentation, we already have concrete molecules that are coming towards the laboratory for tackling the Alzheimer's and the other tough diseases that we cannot solve. And we are leveraging our laboratory. So it's a huge 500 square meter laboratory in Graz that allows us to test this in a laboratory. So we are not only a SaaS or a computer play, we are really trying to develop a next generation of pharma companies where everything is done computationally, but then we also do the molecules in a laboratory. So yeah, it's we are also slowly, I think we're going to have official announcements towards end of this month, beginning of next. We have slowly closed our seed round. It's going to allow us to proceed with our R&D, which we are mainly focused on. So out of the 20 employees, majority are actually PhDs doing research, and that's where our focus lies. So it's not re-implementing or taking something that's out there. We are really trying to do research as we are developing a product.
Yeah, that sounds quite sophisticated. Martin sent us a question. He's saying, like, what was your best achievement in practice using this methodology?
Right. So, as I said, if you go to our company website, you will see that we already have concrete. Names I forget because they are specific. We already have concrete molecules that are developed using this methodology. So, we are already, converging towards preclinical, clinical, and we have moved from the computer and there's concrete outputs. Also importantly to say, we are pretty young. Approximately we are 1 year old. So I think the real outputs are still yet to come. This has not been in development for that much.
Okay, thank you. Thank you, Noah, very much for your presentation and your overview. I think, as I said in the beginning, it's very interesting also for people who are not, who don't have the domain-specific knowledge here. Quite tough challenges, but yeah, I wish you very good luck for the future, and maybe we see each other again at some other events. So thank you, Noah.
Thank you. Thanks for having me.
Thanks, bye. So this was our last session for today. Quite intensive, but very interesting. Before we close this stream, just 2 reminders. One is, if you are looking for a developer job, please check out WeAreDevelopers.com. There is a lot of jobs from the European market, and many of them already with upfront salary information. And second thing, don't miss our JavaScript Congress at the end of November. We have really cool speakers. You can watch them under this link, bit.ly/JSCongress21, or just look it up on the website. I'm sure there is something in for you as well, especially if you are into JavaScript or any of the frameworks, tools, libraries, and so on and so on. With that said, that's it for today, but not for this year. We have more and more live sessions. So next week, we already have our next event. Check it out on the website. It's about DevOps best practices. Very interesting. Tune in and see you next week again. Bye-bye.
Hello everyone, I'm Albert and welcome to adding AI or ML to your automations with AI Center. What ML models does AI Center offer? Great question. AI Center offers more than 25 pre-built ML models in document processing, object detection, text classification, sentiment analysis, entity recognition, demand forecasting, anomaly detection, and many more. If you want to use your own ML models, AI Center operates exactly how it would with a pre-built model.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.